If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. A journey through the galactic heart. Beneath the canopy of the night sky, a river of light flows across the heavens. A tapestry of stars, gas, and dust forming the great celestial wonder we call the Milky Way. For centuries, humanity gazed at this band of luminescence with awe and mystery, crafting myths and stories to explain its existence. Yet, the truth of the Milky Way, our cosmic home, is even more remarkable than the legends. Today, we embark on a journey through the galactic heart, unraveling its intricacies, from its spiral structure to the countless phenomena hidden within its expanse. The Milky Way is a barred spiral galaxy, an immense rotating system of stars, stellar remnants, interstellar gas, and dark matter bound together by gravity. It spans roughly 100,000 light-years across, a colossal wheel of existence that houses our solar system within one of its quieter neighborhoods. Positioned about 27,000 light-years from the galactic center, our vantage point offers an insider's view of this cosmic marvel. But what truly defines the Milky Way? To begin answering this, we must imagine peeling back the layers of a structure as complex as it is beautiful. The galactic disk, a defining feature of the Milky Way, is where the majority of its stars reside. It's a flat, pancake-like region dotted with spiral arms that extend outward like tendrils. Each arm brims with vibrant activity, star-forming regions lighting up like cosmic beacons. These arms, which include the Sagittarius arm and the Perseus arm, are not physical structures in the traditional sense. Instead, they are density waves, areas where stars and gas bunch up, forming a pattern as the galaxy rotates. These waves act as cosmic nurseries, giving birth to stars and shaping the face of our galaxy over millions of years. At the heart of the Milky Way lies its most enigmatic feature, the galactic center, home to a supermassive black hole named Sagittarius A star. This black hole, with a mass equivalent to 4 million suns, exerts a gravitational pull so immense that it orchestrates the movement of stars and gas clouds in its vicinity. The region around it is chaotic, filled with intense radiation, high-energy particles, and some of the densest star clusters known. Observing this turbulent heart required humanity to innovate. By harnessing the power of radio, infrared, and X-ray astronomy, scientists have pieced together a vivid portrait of this invisible giant lurking in our galaxy's core. Surrounding the disk and its central bulge is the galactic halo, a sparse and ancient region dominated by older stars and mysterious dark matter. Unlike the bustling activity within the disk, the halo is quiet, a remnant of the galaxy's formation billions of years ago. It is within this halo that we find globular clusters, compact groups of tens of thousands of stars, relics from the Milky Way's earliest epochs. These clusters serve as living fossils, offering insights into the processes that shaped our galaxy in its infancy. But how did the Milky Way come to be? Its story begins roughly 13.6 billion years ago, in the aftermath of the Big Bang. As the universe expanded and cooled, regions of slightly higher density began to collapse under gravity, forming the first stars and galaxies. The Milky Way likely started as a small, irregular collection of stars and gas, gradually growing through mergers with other protogalaxies. Over time, it developed its distinct spiral shape, driven by gravitational forces and the dance of cosmic matter. Even today, the Milky Way continues to evolve. Its spiral arms are not static. They shift and change over millions of years, influenced by the galaxy's rotation and the gravitational pull of nearby galaxies. Our closest companions, the Magellanic Clouds, are slowly being torn apart by the Milky Way's gravity, their stellar material forming a bridge known as the Magellanic Stream. This process is a testament to the galaxy's dynamic nature, a place of constant change amidst the vastness of space. The study of the Milky Way has been a journey of technological and intellectual leaps. Early astronomers, armed only with their eyes and rudimentary telescopes, could only speculate about its structure. It wasn't until the 20th century, with the advent of powerful optical and radio telescopes, that we began to grasp its true form. The discovery of other galaxies revealed that the Milky Way was not unique, but part of a grander cosmic tapestry. This realization forever changed our understanding of our place in the universe. Perhaps the most humbling aspect of the Milky Way is its role as a cradle for life. Within its spiral arms, stars form and die, scattering the elements necessary for life into the interstellar medium. These elements, forged in the hearts of stars and spread across the galaxy by supernovae, eventually coalesce to form new stars, planets, and potentially life itself. Our own solar system owes its existence to this cosmic cycle of creation and destruction, a cycle that has played out countless times across the galaxy's history. As we delve deeper into the mysteries of the Milky Way, one question looms large. Are we alone? The galaxy's sheer size and diversity make it a fertile ground for the search for extraterrestrial life. With hundreds of billions of stars, many of which host planetary systems, the potential for finding habitable worlds or even intelligent civilizations is tantalizingly high. Yet, despite decades of exploration and observation, the question remains unanswered, a reminder of the vastness and complexity of the universe. The journey through the Milky Way is far from over. With each passing decade, new technologies and missions expand our horizons, revealing more of the galaxy's secrets. The Gaia Space Observatory, for instance, is mapping the positions and movements of over 1 billion stars, creating an unprecedented three-dimensional view of our galactic home. Meanwhile, the James Webb Space Telescope promises to peer into the galaxy's most hidden regions, uncovering phenomena invisible to previous generations of astronomers. The Milky Way is not just a galaxy. It is a cosmic storybook, each star and nebula a chapter in a narrative that spans billions of years. It is a place of wonder and mystery, a microcosm of the universe's vast complexity. As we continue to explore its depths, we are reminded of our own small, yet significant role in this grand cosmic saga, a species born of stardust, looking back at the stars from which it came. A journey through the galactic heart. Beneath the canopy of the night sky, a river of light flows across the heavens, a tapestry of stars, gas, and dust forming the great celestial wonder we call the Milky Way. For centuries, humanity gazed at this band of luminescence with awe and mystery, crafting myths and stories to explain its existence. Yet, the truth of the Milky Way, our cosmic home, is even more remarkable than the legends. Today, we embark on a journey through the galactic heart, unraveling its intricacies, from its spiral structure to the countless phenomena hidden within its expanse. The Milky Way is a barred spiral galaxy, an immense rotating system of stars, stellar remnants, interstellar gas, and dark matter bound together by gravity. It spans roughly 100,000 light-years across, a colossal wheel of existence that houses our solar system within one of its quieter neighborhoods. Positioned about 27,000 light-years from the galactic center, our vantage point offers an insider's view of this cosmic marvel. But what truly defines the Milky Way? To begin answering this, we must imagine peeling back the layers of a structure as complex as it is beautiful. The galactic disk, a defining feature of the Milky Way, is where the majority of its stars reside. It's a flat, pancake-like region dotted with spiral arms that extend outward like tendrils. Each arm brims with vibrant activity, star-forming regions lighting up like cosmic beacons. These arms, which include the Sagittarius arm and the Perseus arm, are not physical structures in the traditional sense. Instead, they are density waves, areas where stars and gas bunch up, forming a pattern as the galaxy rotates. These waves act as cosmic nurseries, giving birth to stars and shaping the face of our galaxy over millions of years. At the heart of the Milky Way lies its most enigmatic feature, the galactic center, home to a supermassive black hole named Sagittarius A star. This black hole, with a mass equivalent to 4 million suns, exerts a gravitational pull so immense that it orchestrates the movement of stars and gas clouds in its vicinity. The region around it is chaotic, filled with intense radiation, high-energy particles, and some of the densest star clusters known. Observing this turbulent heart required humanity to innovate. By harnessing the power of radio, infrared, and X-ray astronomy, scientists have pieced together a vivid portrait of this invisible giant lurking in our galaxy's core. Surrounding the disk and its central bulge is the galactic halo, a sparse and ancient region dominated by older stars and mysterious dark matter. Unlike the bustling activity within the disk, the halo is quiet, a remnant of the galaxy's formation billions of years ago. It is within this halo that we find globular clusters, compact groups of tens of thousands of stars, relics from the Milky Way's earliest epochs. These clusters serve as living fossils, offering insights into the processes that shaped our galaxy in its infancy. But how did the Milky Way come to be? Its story begins roughly 13.6 billion years ago, in the aftermath of the Big Bang. As the universe expanded and cooled, regions of slightly higher density began to collapse under gravity, forming the first stars and galaxies. The Milky Way likely started as a small, irregular collection of stars and gas, gradually growing through mergers with other protogalaxies. Over time, it developed its distinct spiral shape, driven by gravitational forces and the dance of cosmic matter. Even today, the Milky Way continues to evolve. Its spiral arms are not static. They shift and change over millions of years, influenced by the galaxy's rotation and the gravitational pull of nearby galaxies. Our closest companions, the Magellanic Clouds, are slowly being torn apart by the Milky Way's gravity, their stellar material forming a bridge known as the Magellanic Stream. This process is a testament to the galaxy's dynamic nature, a place of constant change amidst the vastness of space. The study of the Milky Way has been a journey of technological and intellectual leaps. Early astronomers, armed only with their eyes and rudimentary telescopes, could only speculate about its structure. It wasn't until the 20th century, with the advent of powerful optical and radio telescopes, that we began to grasp its true form. The discovery of other galaxies revealed that the Milky Way was not unique, but part of a grander cosmic tapestry. This realization forever changed our understanding of our place in the universe. Perhaps the most humbling aspect of the Milky Way is its role as a cradle for life. Within its spiral arms, stars form and die, scattering the elements necessary for life into the interstellar medium. These elements, forged in the hearts of stars and spread across the galaxy by supernovae, eventually coalesce to form new stars, planets, and potentially life itself. Our own solar system owes its existence to this cosmic cycle of creation and destruction, a cycle that has played out countless times across the galaxy's history. As we delve deeper into the mysteries of the Milky Way, one question looms large. Are we alone? The galaxy's sheer size and diversity make it a fertile ground for the search for extraterrestrial life. With hundreds of billions of stars, many of which host planetary systems, the potential for finding habitable worlds or even intelligent civilizations is tantalizingly high. Yet, despite decades of exploration and observation, the question remains unanswered, a reminder of the vastness and complexity of the universe. The journey through the Milky Way is far from over. With each passing decade, new technologies and missions expand our horizons, revealing more of the galaxy's secrets. The Gaia Space Observatory, for instance, is mapping the positions and movements of over 1 billion stars, creating an unprecedented three-dimensional view of our galactic home. Meanwhile, the James Webb Space Telescope promises to peer into the galaxy's most hidden regions, uncovering phenomena invisible to previous generations of astronomers. The Milky Way is not just a galaxy. It is a cosmic storybook, each star and nebula a chapter in a narrative that spans billions of years. It is a place of wonder and mystery, a microcosm of the universe's vast complexity. As we continue to explore its depths, we are reminded of our own small yet significant role in this grand cosmic saga, a species born of stardust, looking back at the stars from which it came. Galactic spiral arms, stretching across the vast plain of the Milky Way. The spiral arms form one of the most iconic features of our galaxy, gracefully winding outward from the galactic center. These arms, glowing with the light of countless stars and nebulae, are not only visually stunning, but are also the bustling hubs of stellar activity. Despite their prominence, the true nature and formation of spiral arms have puzzled astronomers for decades. What are they made of? How do they form? And why do they persist in their elegant patterns, seemingly defying the chaos of the universe? The Milky Way, like other barred spiral galaxies, owes its distinctive shape to a delicate interplay of gravitational forces, motion, and density variations. The spiral arms themselves are not solid structures. Rather, they are regions of higher density within the galactic disk. This phenomenon, known as a density wave, means that while the stars and gas clouds within the arms move, the spiral pattern remains relatively stable over time. Picture a cosmic traffic jam. Just as cars slow down and bunch up on a busy highway, stars and gas clouds accumulate in these density waves as they orbit the galactic center. These regions of increased density trigger a cascade of cosmic events. The compression of gas clouds within the arms ignites the birth of new stars, lighting up the spiral patterns with clusters of young, luminous stars. This continuous cycle of star formation breathes life into the spiral arms, ensuring they remain vibrant and visible. The Milky Way is believed to have 4 primary spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. Additionally, there are minor arms and spurs, including the Orion arm, where our solar system resides. The Orion arm, often considered a minor branch, offers a tranquil vantage point compared to the bustling regions of the main arms. From this location, we gaze outward at the galaxy's grandeur, a privileged perspective that has allowed humanity to study the Milky Way with relative clarity. Each spiral arm tells its own story, a narrative of stellar birth, evolution, and death. Take the Perseus arm, for instance. Spanning vast distances, it is home to some of the most active star-forming regions in the galaxy. Massive clouds of gas and dust, like the California Nebula and the Heart and Soul Nebula, serve as nurseries for new stars. These regions are also rich in young, hot stars whose intense radiation shapes their surroundings, creating stunning nebular structures that glow in vibrant hues. Similarly, the Sagittarius arm is a treasure trove of galactic wonders. This arm contains iconic celestial landmarks such as the Eagle Nebula, famous for its pillars of creation, and the Lagoon Nebula, a vast region of star formation visible even with amateur telescopes. These sites are not just visually spectacular. They also reveal critical insights into the processes that govern the life cycles of stars and the evolution of the galaxy. One of the enduring mysteries of spiral arms lies in their persistence. If stars and gas clouds are constantly moving, why don't the arms disperse over time? The answer lies in the nature of the density waves themselves. Unlike the material within them, the waves are stable patterns that propagate through the galactic disk. This discovery, made in the mid-20th century, was a breakthrough in understanding spiral galaxies. It explained why the arms do not wind up into tighter spirals as the galaxy rotates, a puzzle known as the winding problem. Interestingly, the spiral arms also play a crucial role in the Milky Way's ecosystem. By concentrating gas and dust, they act as cosmic incubators, fostering the conditions necessary for star formation. Without these arms, the galaxy would lack the dynamic interplay of creation and destruction that defines its character. Stars born within the arms eventually drift away, enriching the surrounding interstellar medium with heavy elements produced during their lifetimes. This process ensures that subsequent generations of stars, and the planets that form around them, have the building blocks for complex chemistry, and perhaps life itself. The arms are not immune to disruption. Interactions with nearby galaxies, such as the Magellanic Clouds, exert gravitational forces that can tug at the Milky Way structure. These interactions create ripples in the disk, altering the shape and motion of the spiral arms. While these disturbances might seem chaotic, they also contribute to the galaxy's evolution, ensuring that the spiral pattern remains dynamic and ever-changing. Observing the spiral arms presents unique challenges. From our position within the galactic disk, much of the structure is obscured by interstellar dust. However, advancements in technology have allowed astronomers to map the arms with remarkable precision. Infrared telescopes, capable of peering through the dust, reveal the distribution of stars and gas. Meanwhile, radio astronomy provides insights into the cold, dense regions of molecular gas where new stars are born. Missions like Gaia, which tracks the motions of over 1 billion stars, have further refined our understanding of the Milky Way's intricate structure. One of the most fascinating discoveries about spiral arms is their relationship with dark matter. This invisible substance, which makes up a significant portion of the galaxy's mass, plays a critical role in shaping the arms. By adding gravitational heft, dark matter helps stabilize the disk and supports the formation of density waves. Without it, the Milky Way might look very different, perhaps more irregular or less structured. Understanding this interplay between visible and invisible matter is key to unlocking the secrets of our galaxy. The study of spiral arms also extends beyond the Milky Way. By comparing our galaxy to others in the universe, astronomers gain valuable context. Some galaxies, like the majestic Andromeda, share the Milky Way's barred spiral structure, while others display wildly different forms. Grand designs with tightly wound arms, flocculent spirals with a patchy appearance, or even galaxies with no discernible structure at all. These comparisons highlight the diversity of galactic architecture and offer clues about the forces that shape them. As we continue to explore the spiral arms, they remind us of the interconnectedness of the cosmos. From the dense star clusters at their cores to the vast, empty spaces between, the arms represent the full spectrum of galactic life. They are both the cradles of creation and the stages where stars live out their destinies, enriching the galaxy with each passing generation. For humanity, the spiral arms are more than just a feature of the Milky Way. They are a source of endless inspiration. They are the backdrop against which we gaze at the night sky, their faint glow a reminder of the galaxy's grandeur. They are the nurseries where stars are born, their light illuminating the path to understanding our cosmic origins. And they are the bridges that connect us to the universe, spiraling outward in a dance as old as time itself. The hidden halo. Beyond the visible splendor of the Milky Way's spiral arms and glowing galactic core lies a hidden and enigmatic component of our galaxy, the halo. This vast, faint structure surrounds the Milky Way, extending far beyond its luminous disk, and it is one of the most puzzling and critical elements of our galaxy's architecture. Unlike the bright and dynamic regions of the galaxy, the halo is elusive, composed of dark matter, ancient stars, and other mysterious components that silently influence the Milky Way's form and behavior. The halo is not readily visible to the naked eye, or even through conventional telescopes. It exists as a dim, spherical region enveloping the galactic disk and bulge, stretching out to distances exceeding 300,000 light-years. Within this halo lies a sparse scattering of stars, globular clusters, and most intriguingly, a vast quantity of unseen mass, dark matter, that holds the galaxy together. Its ethereal presence might lack the dramatic beauty of the spiral arms, but its role is no less critical. Without the halo, the Milky Way as we know it would not exist. The stars within the halo are some of the oldest in the galaxy, relics of an era when the universe was young. These stars, often found in globular clusters, are chemically distinct from those in the disk. They contain fewer metals, the astronomers' term for elements heavier than helium, because they formed before such elements were abundant in the universe. By studying these ancient stars, scientists can trace the Milky Way's early history and gain insights into its formation. Globular clusters, dense collections of hundreds of thousands of stars, are among the halo's most striking features. These clusters orbit the galactic center in a spherical distribution, like celestial fossils preserving the conditions of the early universe. Each globular cluster is a time capsule, holding clues about the processes that shaped the galaxy billions of years ago. Observing these clusters has led to significant breakthroughs in our understanding of stellar evolution and the Milky Way's origin story. However, the most perplexing component of the halo is its dark matter. This invisible substance accounts for the majority of the halo's mass and exerts a powerful gravitational pull on the galaxy. Dark matter's existence is inferred from its effects on the motion of stars and gas in the Milky Way. Without it, the galaxy's rotation speeds would not match the predictions based on visible matter alone. Dark matter forms a kind of gravitational scaffold, shaping the galaxy's structure and influencing its evolution. Despite its significance, the nature of dark matter remains one of the greatest mysteries in physics. It does not emit, absorb, or reflect light, making it undetectable by traditional observational methods. Scientists have proposed numerous theories about its composition, ranging from exotic particles to primordial black holes, but definitive answers have yet to be found. The search for dark matter is a central focus of modern astrophysics, with experiments on Earth and in space working to uncover its secrets. The halo is not static. It is a dynamic and interactive region. One of its most fascinating features is the presence of stellar streams, long, ribbon-like structures formed when smaller galaxies are torn apart by the Milky Way's gravity. These streams are the remnants of ancient galactic mergers, providing a window into the Milky Way's tumultuous past. The most famous of these is the Sagittarius Stream, created as the Milky Way slowly consumes the Sagittarius dwarf galaxy. Observing these streams allows astronomers to reconstruct the history of galactic collisions and understand how the Milky Way grew over billions of years. In addition to stellar streams, the halo is also home to high-velocity stars, rogue stars traveling at extraordinary speeds. Some of these stars were likely ejected from the galactic center by interactions with the supermassive black hole, Sagittarius A*, while others may have been accelerated during collisions with smaller galaxies. These hypervelocity stars are rare, but provide valuable insights into the gravitational forces at work within the galaxy. Another enigmatic feature of the halo is its gas content. Observations have revealed vast clouds of hot, ionized gas extending far into the halo, forming what is known as the circumgalactic medium. This gas reservoir contains the building blocks for future star formation and serves as a vital link between the Milky Way and the intergalactic environment. However, the origins and dynamics of this gas remain poorly understood. How does it interact with the galaxy? Is it primarily material left over from the Milky Way's formation? Or is it replenished by galactic interactions and inflows from the cosmic web? These questions drive ongoing research. The halo also plays a crucial role in the stability of the Milky Way. Its dark matter provides the gravitational glue that holds the galaxy together, preventing the disk and its spiral arms from flying apart. Without the halo, the Milky Way structure would be fundamentally different, and its ability to sustain star formation over billions of years might have been compromised. The halo acts as a silent guardian, shaping the galaxy's destiny from behind the scenes. The study of the halo has been revolutionized by advancements in technology. Instruments like the Hubble Space Telescope and the Gaia mission have allowed astronomers to map the positions and motions of stars within the halo with unprecedented precision. Meanwhile, simulations using supercomputers have recreated the formation and evolution of the Milky Way, revealing the critical role of the halo in the galaxy's history. These simulations suggest that the Milky Way has undergone numerous mergers with smaller galaxies, each contributing to the growth and complexity of the halo. One of the most profound implications of the halo is its connection to the cosmic web, the large-scale structure of the universe. The Milky Way's halo is not an isolated entity, but part of a vast network of filaments and nodes composed of galaxies, dark matter, and intergalactic gas. This cosmic web is the framework upon which the universe is built, and the halo serves as a local manifestation of these larger structures. By studying the halo, astronomers gain insights into the broader processes that govern the universe's evolution. Despite the progress made in understanding the halo, much remains unknown. Its elusive nature and complex interactions present significant challenges, but they also make it one of the most exciting frontiers in astronomy. As new technologies emerge, from next-generation telescopes to advanced simulations, the secrets of the halo will continue to be revealed, piece by piece. The hidden halo of the Milky Way is a reminder of the unseen forces that shape the cosmos. It is a testament to the intricate and interconnected nature of the universe, where the visible and invisible coexist in a delicate balance. As we explore this enigmatic realm, we are reminded of the vastness of what lies beyond our sight and the endless mysteries waiting to be uncovered. The Milky Way's cosmic neighbors. The Milky Way is not an isolated island in the cosmos. It exists as part of a bustling community of galaxies, interacting, colliding, and influencing one another over billions of years. This cosmic neighborhood, known as the local group, is a small but dynamic cluster of galaxies bound together by gravity, spanning a region approximately 10 million light-years across. Understanding the Milky Way's relationships with its nearest companions reveals much about the forces shaping not only our galaxy, but also the broader universe. The local group contains over 80 galaxies of varying sizes and types, ranging from sprawling spirals to tiny dwarf galaxies. At its center are three dominant members: the Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. These three form a gravitationally bound system that dictates the behavior and evolution of the smaller galaxies in the group. While the Milky Way and Andromeda are the titans of the local group, their interactions with the surrounding galaxies are anything but subtle. Among the Milky Way's closest companions are the Magellanic Clouds, two irregular dwarf galaxies visible in the southern hemisphere's night sky. The Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC, are in a dance with the Milky Way, their orbits distorted by its immense gravitational pull. This interaction creates tidal forces that strip gas and stars from the Magellanic Clouds, forming streams of material, such as the Magellanic Stream, a sprawling ribbon of hydrogen gas stretching tens of thousands of light-years. The Magellanic Clouds play a significant role in the Milky Way's evolution. They are sources of fresh material, supplying gas that fuels star formation in the galactic disk. However, their interactions also leave marks of disruption, stirring up the Milky Way structure. The LMC, in particular, is believed to be on a trajectory that will eventually lead to its collision with the Milky Way, a process that will reshape both galaxies over millions of years. While the Magellanic Clouds are among the most prominent companions, the Milky Way is surrounded by a swarm of smaller dwarf galaxies. These faint galaxies, such as the Sagittarius Dwarf Spheroidal Galaxy and the Draco Dwarf, orbit the Milky Way like satellites. Many of them are being torn apart by its gravity, their stars and gas streams merging with the Milky Way's halo. This process of galactic cannibalism is a natural part of a galaxy's evolution, allowing larger galaxies to grow by consuming smaller ones. One of the most striking examples of this process is the ongoing interaction with the Sagittarius Dwarf Galaxy. This small, elongated galaxy has been captured by the Milky Way's gravity and is currently being stripped of its stars and gas. These remnants form stellar streams that arc across the sky, blending into the Milky Way's halo. These streams are not just remnants of destruction. They provide valuable clues about the Milky Way's gravitational field and its dark matter halo. Beyond the Milky Way's immediate vicinity lies the Andromeda Galaxy, our closest large neighbor and the largest member of the local group. Andromeda, located approximately 2.5 million light-years away, is a spiral galaxy much like our own, though slightly larger. It shares many features with the Milky Way, including a barred structure, spiral arms, and a supermassive black hole at its core. However, what makes Andromeda truly fascinating is its impending collision with the Milky Way. The Andromeda Galaxy is hurtling toward us at a speed of about 110 kilometers per second, a cosmic rendezvous predicted to occur in roughly 4.5 billion years. This collision will be a transformative event, creating a new galaxy often referred to as Milkomeda. Despite the dramatic terminology, such galactic mergers are not violent in the way one might imagine. The vast distances between stars mean that direct collisions between individual stars are unlikely. Instead, the interaction will reshape the structure of both galaxies, flinging stars into new orbits and triggering bursts of star formation as gas clouds collide. The Triangulum Galaxy, the third largest member of the local group, plays a subtler role. It is a smaller spiral galaxy located near Andromeda, and the two are gravitationally linked. While Triangulum does not directly interact with the Milky Way, its relationship with Andromeda influences the dynamics of the local group. Understanding these interactions helps astronomers piece together the history of this galactic neighborhood. The local group itself is part of an even larger structure called the Virgo supercluster, a vast collection of galaxy groups and clusters spanning hundreds of millions of light-years. This supercluster is just one node in the cosmic web, the large-scale structure of the universe. Within this web, Galaxies are connected by filaments of dark matter and gas, forming a network that underpins the distribution of matter in the cosmos. The local group's place within this web influences its motion and the interactions between its galaxies. Studying the Milky Way's neighbors is more than an exercise in cosmic cartography. It provides critical insights into the processes that govern galaxy formation and evolution. The interactions between galaxies drive the redistribution of gas, stars, and dark matter, shaping their structures over time. These interactions also influence the rate of star formation, the growth of supermassive black holes, and the chemical enrichment of the universe. The relationships within the local group highlight the interconnectedness of the cosmos. No galaxy exists in isolation. Each one is shaped by its neighbors and the larger structures to which it belongs. For the Milky Way, these relationships have been a driving force in its history, from the formation of its halo through mergers to the replenishment of its star-forming regions by interactions with dwarf galaxies. In addition to their scientific significance, the Milky Way's cosmic neighbors inspire a sense of wonder. They remind us of the vastness and complexity of the universe, where even a local cluster of galaxies encompasses millions of light years. They offer a glimpse of the future, a preview of the cosmic ballet that will continue long after humanity has departed the stage. As we explore our galaxy's connections to its neighbors, we are reminded of the profound unity of the cosmos. The Milky Way is but one member of a vast, interconnected system, a single note in the symphony of the universe. Through these relationships, we come to understand not only the nature of galaxies, but also the grand, overarching forces that shape the cosmos itself. Star factories in the galaxy. The Milky Way, with its spiraling arms and luminous core, is much more than a serene spectacle in the night sky. It is a dynamic ecosystem, continuously creating and recycling stars in vast regions known as star-forming regions or star factories. These stellar nurseries are the engines of the galaxy, where gas and dust come together under the influence of gravity to birth new stars. Each of these regions is a testament to the creativity of the cosmos, illuminating the night sky and fueling the Milky Way's evolution. At the heart of every star factory lies a complex interplay of physical processes. Stars begin their lives in massive clouds of gas and dust called molecular clouds. These regions are cold and dense, with temperatures just a few degrees above absolute zero. Shielded from external radiation by thick layers of dust, molecular clouds provide the ideal environment for the formation of hydrogen molecules, the primary ingredient for star creation. When a portion of a cloud becomes unstable due to gravitational collapse, a nearby supernova shockwave, or turbulence, it begins to fragment and contract, setting the stage for star formation. One of the most iconic star factories in the Milky Way is the Orion Nebula, located roughly 1,300 light-years away in the Orion arm of the galaxy. This nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is a hotbed of stellar activity. Observations of the Orion Nebula have revealed hundreds of young stars in various stages of development, surrounded by swirling disks of gas and dust that may eventually form planetary systems. It is a microcosm of the processes that have shaped stars and planets across the galaxy. Similarly, the Carina Nebula, located in the southern sky, showcases the raw power and beauty of star formation. Home to some of the most massive stars in the galaxy, including the enigmatic Eta Carinae, this nebula is a cauldron of intense radiation, stellar winds, and gravitational forces. The interplay of these forces sculpts the surrounding gas into intricate shapes while triggering the formation of new stars. The process of star formation is far from uniform. In regions like the Eagle Nebula, famous for its pillars of creation, towering columns of gas and dust serve as the incubators for new stars. These pillars are shaped by the intense radiation from nearby massive stars, which erode the surrounding material while compressing the gas within, initiating the formation of new stars. This dual process of destruction and creation is a hallmark of star-forming regions, highlighting the cyclical nature of the cosmos. Not all star factories are as dramatic as the Orion or Carina nebulae. Some are quiet and unassuming, hidden behind thick layers of interstellar dust. Infrared telescopes, such as the Spitzer Space Telescope and the James Webb Space Telescope, have revolutionized our ability to observe these regions, peering through the dust to reveal the birthplaces of stars. These observations have uncovered regions of intense activity in the Milky Way, such as the central molecular zone near the galactic center, where the density of gas and the gravitational forces are exceptionally high. Star formation is not limited to nebulae within the Milky Way. Stellar nurseries are scattered across the galaxy, often concentrated in the spiral arms where gas and dust are most abundant. These regions, illuminated by young, hot stars, light up the arms like beacons, revealing the ongoing processes that keep the galaxy alive. The rate of star formation varies across the Milky Way, with some regions experiencing bursts of activity while others remain dormant. Massive stars play a pivotal role in shaping star-forming regions. Although they are relatively short-lived, their intense radiation and powerful stellar winds influence the surrounding environment, creating feedback loops that can either trigger or suppress the formation of new stars. When these stars reach the end of their lives in spectacular supernova explosions, they scatter heavy elements into the interstellar medium, enriching the galaxy with the building blocks for planets and life. The interplay between star formation and the broader galactic environment is a subject of intense study. Observations of the Milky Way reveal that star formation is not an isolated process, but one that is deeply interconnected with the galaxy's overall structure and dynamics. For instance, the spiral arms act as density waves, compressing gas and dust as they rotate, which initiates the formation of stars. Meanwhile, interactions with neighboring galaxies, such as the Magellanic Clouds, can inject fresh material into the Milky Way, fueling new episodes of star formation. The life cycles of stars are intricately tied to the concept of cosmic recycling. As stars form, live out their lifetimes, and die, they release material back into the galaxy. This process is evident in regions like the Veil Nebula, the remnants of a supernova explosion. The shock waves from such events compress surrounding gas, creating pockets of intense activity where new stars are born. Over billions of years, this cycle has transformed the Milky Way from a primordial galaxy of hydrogen and helium into a rich tapestry of elements capable of supporting complex chemistry and life. While much has been learned about star formation, many mysteries remain. One of the most pressing questions is what determines the rate of star formation in a galaxy. Observations show that the Milky Way forms roughly 1 to 2 solar masses of stars per year, a relatively modest rate compared to some galaxies that experience starbursts, forming hundreds of solar masses per year. Understanding what governs these rates, from the availability of gas to the influence of dark matter, is a key challenge for astronomers. The tools and techniques used to study star factories continue to evolve. Missions like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, provide unprecedented detail, capturing the birth of stars and planets in exquisite resolution. These observations not only reveal the mechanisms of star formation, but also provide insights into the conditions that lead to the formation of planetary systems like our own. Star factories are more than just regions of scientific interest. They are reminders of the Milky Way's vitality and creativity. They are the places where the universe's raw materials are transformed into the luminous objects that populate the night sky. Each new star that emerges from these cosmic nurseries adds to the galaxy's brilliance, contributing to the grand tapestry of the cosmos. As we peer into these regions, we are reminded of our own origins. The sun, like all stars, was born in a similar environment, emerging from a cloud of gas and dust billions of years ago. The elements that make up our planet, and even our bodies, were forged in the hearts of stars that lived and died long before our solar system formed. The star factories of the Milky Way are not just places of creation. They are the engines of cosmic continuity, linking the past, present, and future in a never-ending cycle of stellar evolution. Exoplanets of the Milky Way. For centuries, the stars have beckoned to humanity as a realm of infinite possibilities, their faint light hinting at the potential for worlds beyond our own. With the dawn of modern astronomy, this long-held dream has become a reality. We now know that the Milky Way is teeming with planets orbiting stars across its spiral arms. These exoplanets, as they are called, represent some of the most exciting frontiers in science, offering tantalizing glimpses of diverse worlds and the possibility of life beyond Earth. The first confirmed discovery of an exoplanet came in 1992, when astronomers detected planets orbiting a pulsar, a rapidly spinning neutron star. This discovery was groundbreaking, revealing for the first time that planets existed outside our solar system. Just a few years later, the first exoplanet orbiting a Sun-like star, 51 Pegasi b, was identified. This hot Jupiter, a gas giant orbiting extremely close to its star, opened the floodgates for exoplanet exploration, marking the beginning of a golden age of discovery. Today, thanks to missions like Kepler, TESS, Transiting Exoplanet Survey Satellite, and a host of ground-based observatories, we have confirmed the existence of over 5,500 exoplanets, with thousands more awaiting validation. These planets come in an astonishing variety of types, sizes, and orbital configurations, many of which challenge our understanding of planetary formation and dynamics. One of the most surprising discoveries in the study of exoplanets is their diversity. Planets in the Milky Way range from gas giants hundreds of times the size of Earth to rocky, Earth-sized worlds, and even smaller objects. They orbit their stars at distances that defy expectations. Some cling precariously close, completing an orbit in mere hours, while others wander at vast distances, barely bound by their star's gravity. There are even rogue planets, worlds that drift through the galaxy untethered to any star, remnants of cosmic upheavals. Among the most intriguing types of exoplanets are the so-called super-Earths and mini-Neptunes, which have no direct analog in our solar system. Super-Earths are rocky planets larger than Earth but smaller than Neptune, with masses that allow them to retain thicker atmospheres. Mini-Neptunes, on the other hand, are smaller versions of the gas giants in our solar system, often shrouded in thick envelopes of hydrogen and helium. These classes of planets are among the most common in the galaxy, yet their nature and formation remain hotly debated. One of the most significant goals of exoplanet science is identifying potentially habitable worlds, planets where conditions might support liquid water and, by extension, life as we know it. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where temperatures are just right for water to remain liquid. While this is a critical criterion, habitability depends on many other factors, including a planet's atmosphere, magnetic field, and geological activity. The discovery of Earth-sized exoplanets within their stars' habitable zones has been a highlight of recent years. Kepler 452b, often dubbed Earth's cousin, orbits a star similar to the Sun and is located in its habitable zone. Similarly, the TRAPPIST-1 system, a remarkable collection of 7 Earth-sized planets orbiting a dim red dwarf star, has captivated scientists. At least 3 of these planets lie within the habitable zone, making the system a prime target for studying atmospheres and searching for biosignatures. Red dwarf stars, like TRAPPIST-1, are particularly intriguing in the search for life. These stars are smaller and cooler than the Sun, meaning their habitable zones are much closer to the star. While this proximity exposes planets to intense stellar flares and radiation, it also makes detecting and studying these planets easier. Red dwarfs are the most common type of star in the Milky Way, suggesting that Earth-like planets may be abundant. The search for life on exoplanets has taken on a new dimension with the advent of advanced telescopes like the James Webb Space Telescope, JWST. JWST and other instruments are equipped to analyze the atmospheres of distant worlds, looking for signs of water vapor, oxygen, methane, and other molecules that could indicate the presence of life. These observations are painstakingly detailed, involving the study of tiny dips in starlight as planets pass in front of their stars, a technique known as transit spectroscopy. The discovery of atmospheres on exoplanets, even those with no immediate signs of life, is a major milestone. For example, the detection of thick, cloudy atmospheres on hot Jupiters, like HD 189733b, has provided insights into the extreme conditions on these worlds. Similarly, the discovery of potentially water-rich atmospheres on mini-Neptunes has opened the door to studying planets that might host exotic forms of life. The implications of exoplanet science extend far beyond the search for life. These discoveries have revolutionized our understanding of planetary formation and the diversity of planetary systems. Before the era of exoplanet discovery, our solar system served as the only template for how planetary systems might look. Now, we know that planetary systems come in configurations that defy this model, such as systems with tightly packed inner planets or those dominated by giant worlds with eccentric orbits. Studying exoplanets also sheds light on the processes that shape their evolution. For instance, many gas giants orbit extremely close to their stars, a phenomenon known as hot Jupiter migration. These planets likely formed farther out in their systems and migrated inward, profoundly altering the dynamics of their surroundings. Understanding these processes helps us piece together the history of not only these distant systems, but also our own solar system. While exoplanet research has achieved remarkable progress, it is still in its infancy. The future promises even more profound discoveries, driven by the development of next-generation observatories like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope. These instruments will be capable of directly imaging Earth-like exoplanets and studying their light in exquisite detail, bringing us closer than ever to answering the age-old question: are we alone in the universe? The hunt for exoplanets is not just a scientific endeavor. It is a journey of imagination and exploration. Each new discovery expands our sense of what is possible in the cosmos, revealing worlds that challenge our assumptions and inspire wonder. From fiery lava planets to frozen rogue worlds drifting in interstellar space, the diversity of exoplanets reminds us of the boundless creativity of the universe. As we continue to explore the Milky Way, the discovery of exoplanets will remain a central chapter in the story of humanity's quest to understand its place in the cosmos. These distant worlds, scattered across the galaxy, are beacons of possibility, inviting us to dream of what might exist beyond the pale blue that we call home. The mystery of the galactic bar. At the heart of the Milky Way, hidden behind vast clouds of interstellar dust, lies an enigmatic structure that shapes the galaxy's very dynamics. The galactic bar. This elongated formation of stars and gas stretches across the central bulge, serving as both a gravitational anchor and a conveyor belt for material moving through the galaxy. While the galactic bar is a defining feature of the Milky Way, its origins, purpose, and influence remain subjects of intense study and intrigue. The galactic bar is not unique to the Milky Way. It is a common feature in many spiral galaxies, particularly those classified as barred spirals. These bars appear to play a significant role in the evolution of their host galaxies, but their precise function and formation are far from fully understood. In the case of the Milky Way, the bar spans roughly 27,000 light-years, making it a dominant feature of the inner galaxy. It is composed of stars, gas, and dust, all rotating in unison around the galactic center. The discovery of the Milky Way's bar was not straightforward. From our vantage point within the galactic disk, the central region of the Milky Way is obscured by dense clouds of gas and dust, making it invisible to optical telescopes. It was only through the use of infrared observations, which can penetrate these obscuring clouds, that the bar's presence was confirmed. The Spitzer Space Telescope and other instruments have since provided detailed maps of the bar, revealing its size, shape, and orientation. One of the most compelling aspects of the galactic bar is its role as a dynamic structure. Unlike the spiral arms, which are regions of higher density that rotate with the galactic disk, the bar is a coherent, elongated feature that exerts a powerful gravitational influence on its surroundings. This influence extends well beyond the bar itself, shaping the motions of stars and gas throughout the inner galaxy. The bar acts as a cosmic traffic controller, directing the flow of gas and stars within the Milky Way. Gas clouds, for instance, are funneled along the bar toward the galactic center, where they accumulate and trigger bursts of star formation. This process helps sustain the activity of the central region, making the galactic bar a key driver of the Milky Way's evolution. At the same time, the bar's gravitational forces can disrupt the orbits of stars in the inner disk, creating complex patterns of motion that are still not fully understood. One of the most intriguing questions about the galactic bar is how it formed. Current theories suggest that bars emerge naturally in spiral galaxies as a result of gravitational instabilities. Over time, The rotation of the galaxy causes the central region to elongate, forming a bar-like structure. This process is influenced by the distribution of mass within the galaxy, including the dark matter halo that surrounds it. While this explanation is widely accepted, the details remain uncertain, and simulations often struggle to replicate the exact conditions that give rise to a bar. The bar's role in shaping the Milky Way extends beyond the central regions. It also influences the spiral arms, creating and sustaining the density waves that define their structure. Observations suggest that the bar's rotation drives these waves outward, ensuring that the spiral arms remain prominent features of the galaxy. This interaction highlights the interconnected nature of the Milky Way, where the dynamics of one region can ripple outward, affecting the entire structure. Interestingly, the galactic bar is not a static feature. Observations indicate that it is slowly rotating, a phenomenon known as pattern speed. This rotation affects the orbits of stars and gas in the inner galaxy, creating resonances where objects become locked into specific patterns of motion. These resonances are thought to be responsible for some of the most striking features of the Milky Way, including the inner rings of stars and gas that encircle the bar. The presence of the bar also has implications for the supermassive black hole at the galactic center, Sagittarius A star. The bar channels material toward the black hole, providing a steady supply of gas and dust that can fuel its activity. While Sagittarius A asterisk is currently in a relatively quiet state, the bar's influence ensures that it remains an active participant in the galaxy's evolution. Periodic surges of material funneled along the bar could lead to dramatic outbursts, illuminating the central region with intense radiation. Despite its significance, the galactic bar is a challenging subject to study. Its structure and dynamics are difficult to observe directly, and much of our knowledge comes from indirect measurements and simulations. Recent advances in technology, such as the Gaia mission, have provided unprecedented data on the motions of stars in the inner galaxy, offering new insights into the bar's influence. These observations are helping to refine our models and deepen our understanding of this enigmatic structure. The study of the galactic bar also has broader implications for our understanding of galaxy evolution. Bars are not unique to the Milky Way. They are found in many spiral galaxies across the universe. By comparing the Milky Way's bar to those in other galaxies, astronomers can identify common patterns and processes, shedding light on the role of bars in shaping galaxies over cosmic time. In many ways, the galactic bar represents a microcosm of the Milky Way itself, a complex, dynamic structure that reflects the interplay of gravity, motion, and matter. It is a reminder that the galaxy is not a static entity, but a living, evolving system, shaped by the forces that govern the universe. As we continue to explore the mysteries of the Milky Way, the galactic bar will remain a focal point, offering clues about the forces that have shaped our galaxy and its place in the cosmos. Stellar archaeology. Deep within the glittering expanse of the Milky Way lies a treasure trove of cosmic history. Each star, from the faintest red dwarf to the most luminous supergiant, serves as a time capsule, preserving the story of the galaxy's evolution. The field of stellar archaeology seeks to unravel these stories, using the chemical compositions, motions, and ages of stars to reconstruct the Milky Way's past. Like piecing together an ancient mosaic, astronomers draw from the clues hidden in starlight to reveal how our galaxy came to be. Stars are born from clouds of gas and dust, and their chemical makeup reflects the conditions of the environment in which they formed. As the universe aged, successive generations of stars enriched the cosmos with heavier elements, or metals, forged in their cores. By studying the metallicity of stars, essentially their abundance of elements heavier than hydrogen and helium, scientists can estimate their ages and place them within the timeline of galactic evolution. The Milky Way is structured like a layered cake of stellar populations, each representing a different epoch of formation. At its center lies the bulge, a densely packed region of ancient stars that holds the oldest relics of the galaxy's past. These stars, often with low metallicities, date back over 10 billion years, to a time when the Milky Way was a chaotic assembly of smaller protogalaxies. Observing the stars in the bulge is akin to peering into the galaxy's primordial heart, offering a glimpse of its earliest stages. Moving outward, The disk of the Milky Way is home to younger stars, including the Sun. Here, metallicities are higher, reflecting the enrichment of the interstellar medium by previous generations of stars. The disk is divided into two main components: the thin disk, where most star formation occurs today, and the thick disk, which harbors older stars with slightly lower metallicities. The differences between these two components provide insights into the processes that shape the galaxy's structure, such as mergers and the dynamics of its spiral arms. Beyond the disk lies the halo, a sparse, spherical region populated by some of the oldest stars in the galaxy. Many of these halo stars are remnants of ancient dwarf galaxies consumed by the Milky Way in its early history. Their orbits, which are often highly eccentric and inclined relative to the disk, bear the imprint of these long-ago mergers. By studying the motions and compositions of halo stars, astronomers can reconstruct the Milky Way's violent adolescence, when it grew through the accretion of smaller systems. One of the most remarkable tools of stellar archaeology is the study of globular clusters. These densely packed groups of tens of thousands to millions of stars are among the oldest objects in the galaxy. Each cluster contains stars that formed at nearly the same time, providing a snapshot of the conditions that prevailed when the cluster was born. By analyzing the ages and metallicities of stars and globular clusters, astronomers can trace the timeline of star formation in the Milky Way and identify key events, such as bursts of activity triggered by galactic mergers. A key aspect of stellar archaeology is the use of spectroscopy, a technique that analyzes the light emitted by stars to determine their chemical compositions. By splitting starlight into its component wavelengths, astronomers can identify the fingerprints of various elements. These fingerprints reveal not only the star's metallicity, but also the specific ratios of elements like carbon, oxygen, and iron, which provide clues about the processes that enrich the star's birthplace. For instance, stars with high ratios of alpha elements, such as oxygen and magnesium, relative to iron, are thought to have formed in environments dominated by supernovae from massive stars. These explosions occur quickly, within millions of years, enriching the surrounding gas with alpha elements. In contrast, stars with higher iron abundances relative to alpha elements likely formed later, after slower processes like Type Ia supernovae began contributing iron to the interstellar medium. The combination of chemical data and stellar motions allows astronomers to map the Milky Way's history in unprecedented detail. Missions like Gaia have been revolutionary in this regard, providing precise measurements of the positions, velocities, and distances of billions of stars. By tracing the orbits of stars backward in time, researchers can identify streams and structures left behind by ancient mergers, piecing together the Milky Way's assembly from smaller protogalaxies. One of the most exciting discoveries in recent years has been the identification of the Gaian-Enceladus event, a massive collision that occurred roughly 10 billion years ago. This event involved a dwarf galaxy, dubbed Gaian-Enceladus, merging with the Milky Way. The debris from this merger is still visible in the form of a distinct population of stars in the halo, with unique chemical signatures and orbital patterns. This discovery has reshaped our understanding of the Milky Way's early evolution, highlighting the importance of mergers in building its structure. Stellar archaeology also sheds light on the broader cosmic context of the Milky Way. By comparing the properties of stars in our galaxy to those in other galaxies, astronomers can identify universal patterns and unique features. For example, the Milky Way's relatively quiescent star formation history contrasts with the more intense activity seen in some starburst galaxies. These comparisons provide insights into the factors that influence galaxy evolution, from dark matter halos to interactions with neighboring systems. Beyond the study of individual stars, stellar archaeology has profound implications for our understanding of the universe. The chemical evolution of galaxies, driven by the lives and deaths of stars, determines the availability of elements essential for life. By tracing the enrichment of the Milky Way over billions of years, we gain a deeper appreciation for the processes that made our existence possible. The heavy elements in our bodies, carbon, oxygen, nitrogen, and more, were forged in the hearts of stars and distributed across the galaxy by supernovae and stellar winds. The field of stellar archaeology is constantly evolving, driven by advancements in technology and theory. Next-generation observatories such as the European Extremely Large Telescope, ELT, and the Vera C. Rubin Observatory promise to uncover even more details about the stars that populate the Milky Way. These instruments will provide higher-resolution spectra, more precise distances, and deeper insights into the galaxy's oldest populations. As we delve deeper into the Milky Way's past, we are reminded that the stars above are not just points of light, but the storytellers of cosmic history. Each star carries within it a record of the processes that shaped our galaxy, from its chaotic beginnings to its present grandeur. Through stellar archaeology, we can reconstruct this epic narrative, connecting the dots between the past and the present, and gaining a greater understanding of our place in the universe. The life cycle of stars. Stars are the engines of the universe, forging elements, illuminating galaxies, and shaping the cosmos with their powerful forces. But their lives, those spanning millions to billions of years, are not eternal. Stars are born, live dynamic and varied existences, and ultimately meet their demise, recycling their material back into the universe. The life cycle of stars is a tale of transformation, driven by the interplay of gravity, nuclear fusion, and cosmic forces. The story begins in the cold, dark regions of space, known as molecular clouds. These clouds, composed primarily of hydrogen and helium, are vast reservoirs of raw material. Within these clouds, regions of higher density can become gravitationally unstable, collapsing under their own weight. This process is often triggered by external events, such as the shockwave from a nearby supernova or the gravitational influence of a passing star. As a cloud fragment collapses, it begins to heat up, forming a protostar, a hot, dense core surrounded by a rotating disk of gas and dust. During this phase, the protostar is shrouded in its cocoon, emitting primarily infrared radiation as it accretes material from its surroundings. Over time, the core temperature and pressure rise, reaching the critical threshold where nuclear fusion ignites. Fusion is the defining process of a star's life. In the core, hydrogen nuclei combine to form helium, releasing immense energy in the process. This energy radiates outward, counteracting the force of gravity and stabilizing the star. The balance between gravity pulling inward and pressure from fusion pushing outward defines the star's main sequence phase, the longest and most stable period of its life. The characteristics of a star during the main sequence depend on its mass. Massive stars burn their fuel quickly, shining brightly but living short lives, often only a few million years. Smaller stars, like red dwarfs, burn their fuel slowly, persisting for tens of billions of years. Our Sun, a medium-mass star, is expected to remain on the main sequence for about 10 billion years, and it is currently halfway through its life. As a star exhausts its hydrogen fuel, it leaves the main sequence and enters the next stage of its evolution. For low to medium-mass stars like the Sun, the core contracts while the outer layers expand, forming a red giant. During this phase, helium fusion ignites in the core, producing heavier elements like carbon and oxygen. The star becomes a luminous, swollen giant, shedding its outer layers into space in the form of stellar winds or planetary nebulae. The remnants of a low to medium-mass star's core become a white dwarf, a dense, Earth-sized object composed primarily of carbon and oxygen. White dwarfs no longer undergo fusion and instead radiate away their residual heat over billions of years, slowly fading into obscurity as black dwarfs, a stage the universe has not yet reached due to its young age. For massive stars, the end is far more dramatic. After burning through their hydrogen and helium, these stars undergo a series of fusion processes, creating heavier and heavier elements in their cores. However, this process halts at iron, as fusing iron consumes energy rather than releasing it. With no outward pressure to counter gravity, the core collapses, triggering a catastrophic supernova explosion. The supernova is one of the most energetic events in the universe, releasing more energy in a few seconds than the sun will emit in its entire lifetime. This explosion blasts the outer layers of the star into space, enriching the interstellar medium with heavy elements like gold, silver, and uranium. These elements, forged in the heart of stars and spread by supernovae, are essential for the formation of planets and life. What remains of the core depends on the mass of the original star. If the core is less than about 3 times the mass of the Sun, it becomes a neutron star, a city-sized object composed almost entirely of neutrons. Neutron stars are incredibly dense, with a teaspoon of their material weighing billions of tons. Some neutron stars emit beams of radiation as they spin, becoming pulsars, cosmic lighthouses that blink in the night sky. For the most massive stars, the core collapses further, forming a black hole. These objects are so dense that not even light can escape their gravity. Black holes profoundly influence their surroundings, warping space-time and consuming nearby material. While black holes are often portrayed as cosmic destroyers, they also play a crucial role in shaping galaxies and driving the dynamics of the universe. The life cycle of stars is deeply interconnected with the cosmos. When stars die, they return their material to the interstellar medium, enriching it with the elements forged in their cores. This recycled material becomes the building blocks for new stars, planets, and eventually life. The Sun and its planets, including Earth, are the products of this cosmic cycle, a lineage that traces back to the death of earlier generations of stars. Stars also influence their environments throughout their lives. Their radiation shapes the surrounding gas, creating nebulae and ionized regions. Stellar winds and supernovae sculpt the interstellar medium, triggering the formation of new stars in some regions while dispersing material in others. These processes drive the evolution of galaxies, ensuring that star formation is an ongoing cycle. The study of stellar evolution has been revolutionized by advancements in technology. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope provide detailed images of stars in every stage of their lives, from protostars hidden in dense clouds to the remnants of supernovae. Meanwhile, computer simulations allow scientists to model the complex physics of stellar interiors and predict their fates. One of the most profound aspects of stellar evolution is its connection to the elements of life. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones were all forged in the cores of stars. This realization underscores the idea that we are made of star stuff, a poetic truth that connects humanity to the cosmos. As we study the life cycles of stars, we gain a deeper understanding of the universe's history and future. Stars are not static entities but dynamic participants in the cosmic story, shaping and being shaped by the environments in which they live. Their births, lives, and deaths are the threads that weave the fabric of the galaxy, illuminating its past and guiding its evolution. The life cycle of stars is a reminder of the universe's grandeur and creativity, a process of constant renewal that ensures the cosmos remains vibrant and ever-changing. Through their light, stars tell the story of the universe, a story that continues to unfold as we explore the depths of the Milky Way and beyond. Cosmic recycling. The universe is a master of renewal. In its vast expanse, nothing is wasted. Every particle of matter, every trace of energy is repurposed, reshaped, and woven into the ongoing tapestry of cosmic evolution. This process, known as cosmic recycling, is the foundation upon which galaxies, stars, planets, and even life itself are built. In the Milky Way, cosmic recycling is an intricate interplay of stellar deaths, interstellar material, and the birth of new celestial objects, a never-ending cycle that binds the galaxy's past, present, and future. At the heart of cosmic recycling is the life and death of stars. Stars are factories of creation, forging elements in their cores through nuclear fusion. Hydrogen, the universe's most abundant element, serves as the initial fuel, combining under immense pressure and temperature to form helium. As stars age and progress through their life cycles, they create heavier elements, from carbon and oxygen to silicon and iron. These elements, essential for the formation of planets and the emergence of life, are locked within the star until it reaches the end of its life. The death of a star is a transformative event, releasing its enriched material back into the galaxy. For low and medium-mass stars, this process occurs as they shed their outer layers, creating stunning planetary nebulae. These nebulae, illuminated by the dying star's core, are colorful, complex structures that spread elements like carbon and nitrogen into the surrounding interstellar medium. The core itself becomes a white dwarf, a remnant that quietly fades over billions of years. Massive stars, however, end their lives in dramatic supernova explosions. These cataclysmic events are not only spectacular to behold, but also vital for cosmic recycling. A supernova releases a tremendous amount of energy, ejecting the star's outer layers into space at incredible speeds. In the process, it creates and disperses elements heavier than iron, such as gold, uranium, and platinum. These elements are rare and valuable, found in the crusts of planets, and even in the atoms that make up our bodies. Without supernovae, the universe would lack the diversity of elements necessary for complex chemistry. The material expelled by dying stars, gas, dust, and newly forged elements, joins the interstellar medium, a vast and dynamic reservoir that fills the galaxy. This medium is far from uniform. It consists of regions of varying density and temperature, from cold molecular clouds to hot, ionized plasma. Over time, gravitational forces, stellar winds, and shockwaves from supernovae shape the interstellar medium, creating pockets of density where new stars can form. These regions are the birthplace of the next generation of stars, continuing the cycle of creation and destruction. One of the most fascinating aspects of cosmic recycling is the role of supernova shockwaves in triggering star formation. When a supernova explodes, its shockwave compresses nearby gas clouds, destabilizing them and initiating gravitational collapse. This process kickstarts the formation of protostars, which will eventually evolve into fully fledged stars. In this way, the death of one star paves the way for the birth of others, demonstrating the interconnected nature of the galaxy. Dust, an often overlooked component of the interstellar medium, plays a crucial role in cosmic recycling. Composed of tiny grains of carbon, silicon, and other elements, dust acts as a catalyst for the formation of molecules, including water and organic compounds. These molecules are essential for the chemistry of life and serve as the building blocks for planets. Dust also absorbs and scatters starlight, creating the dark lanes and glowing regions seen in nebulae and the Milky Way's spiral arms. The recycled material in the interstellar medium doesn't just form stars, it also contributes to the creation of planets. As stars form from collapsing gas clouds, their surrounding material coalesces into rotating disks. Within these protoplanetary disks, dust grains stick together, forming larger and larger bodies until planets emerge. The elements dispersed by previous generations of stars are thus incorporated into these new worlds, providing the raw materials for oceans, atmospheres, and potentially life. The Sun and its planets, including Earth, are products of this cosmic recycling. Billions of years ago, a massive star exploded in a supernova, enriching a nearby gas cloud with heavy elements. This cloud eventually collapsed to form the solar system, embedding its planets with the chemical diversity that makes Earth unique. The carbon in your cells, the calcium in your bones, and the iron in your blood were all forged in stars that lived and died long before the sun was born. Cosmic recycling extends beyond stars and planets. Even galaxies participate in this process, exchanging material with their surroundings. The Milky Way, for example, interacts with its neighbors, such as the Magellanic Clouds, through gravitational forces that strip gas and stars from these smaller galaxies. This material feeds the Milky Way, fueling star formation and enriching the interstellar medium. Similarly, the galaxy itself loses material through powerful outflows driven by supernovae and stellar winds, which eject gas into intergalactic space. These outflows, known as galactic winds, are critical for regulating star formation. By removing gas from the galaxy, they prevent the unchecked creation of stars, maintaining a balance that ensures the Milky Way's longevity. Over time, some of this ejected material may fall back into the galaxy, completing the cycle of recycling on a grander scale. The process of cosmic recycling is not limited to the Milky Way. It is a universal phenomenon that shapes galaxies across the cosmos. Observations of distant galaxies reveal similar cycles of star formation, stellar death, and enrichment of the interstellar medium. These cycles drive the evolution of galaxies, transforming them from primordial clouds of gas into the complex structures we see today. The study of cosmic recycling has been revolutionized by modern astronomy. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have provided breathtaking images of stellar nurseries, planetary nebulae, and supernova remnants, offering glimpses into the processes that drive recycling. Meanwhile, advanced spectroscopy has allowed scientists to analyze the chemical compositions of stars and nebulae, revealing the distribution of elements across the galaxy. Cosmic recycling also has profound implications for the search for life beyond Earth. By understanding how elements essential for life are distributed and recycled, scientists can identify regions of the galaxy where habitable planets are most likely to form. The realization that life depends on the deaths of stars underscores the interconnectedness of all things in the cosmos. In many ways, cosmic recycling is a metaphor for the universe itself, a process of continual renewal and transformation. It highlights the resilience and creativity of the cosmos, where even destruction becomes a source of creation. As we study this cycle, we gain a deeper appreciation for the forces that shaped the Milky Way and the role we play within this grand cosmic story. The galactic center's forbidden zone. Deep within the heart of the Milky Way lies a region so extreme and enigmatic that it has been dubbed the Forbidden Zone. This central region, densely packed with stars, gas, and dark matter, orbits the galaxy's supermassive black hole, Sagittarius A star. For decades, this area remained shrouded in mystery, hidden behind thick veils of interstellar dust and gas. Modern technology, however, has pierced this cosmic curtain, revealing a tumultuous and chaotic environment teeming with phenomena that defy imagination. The galactic center is located approximately 27,000 light-years from Earth, a distance that puts it beyond the reach of optical telescopes due to the dense clouds of dust in the galactic plane. Infrared, radio, and X-ray telescopes, however, have made it possible to study this region, uncovering a realm of intense gravitational forces, high-energy radiation, and exotic celestial objects. At the core of the Forbidden Zone lies Sagittarius A asterisk, the Milky Way's supermassive black hole. With a mass equivalent to about 4 million suns, it dominates the dynamics of the central region. Despite its immense gravity, Sagittarius A asterisk is surprisingly quiet compared to the active black holes at the centers of some other galaxies. It emits relatively modest levels of radiation, leading astronomers to describe it as starving. However, occasional flares of X-rays and infrared light suggest that it is not entirely dormant. These flares occur when material falls into the black hole's event horizon, releasing bursts of energy as it is consumed. Surrounding Sagittarius A asterisk is a dense cluster of stars, many of which are among the most massive and luminous in the galaxy. These stars, known as S-stars, have some of the fastest known orbits in the Milky Way. Observations of their trajectories provided the first definitive evidence of Sagittarius A asterisk's existence, as only a supermassive black hole could account for their incredible speeds. One star, S2, completes an orbit around the black hole in just 16 years, reaching speeds of over 7,000 kilometers per second at its closest approach. The environment around the galactic center is a chaotic maelstrom of activity. The density of stars in this region is millions of times greater than in the vicinity of our Sun. This crowded space results in frequent close encounters and even collisions between stars. Such interactions can eject stars at incredible velocities, creating hypervelocity stars that escape the galaxy entirely. Gas and dust also play a significant role in the dynamics of the Forbidden Zone. Vast molecular clouds, some containing the mass of millions of suns, orbit the galactic center. These clouds are constantly being disrupted by the intense gravitational forces and radiation in the region. Occasionally, a cloud ventures too close to Sagittarius A asterisk, where tidal forces stretch and tear it apart, producing brilliant flares as the material spirals into the black hole. The galactic center is also home to mysterious objects that challenge our understanding of astrophysics. One such category is the G-objects, which appear to be hybrid entities combining characteristics of stars and gas clouds. These objects are stretched and distorted as they approach Sagittarius A asterisk, suggesting that they are interacting with the black hole's immense gravitational field. The true nature of G-objects remains a mystery, with theories ranging from them being stars enveloped in thick gas clouds to entirely new astrophysical phenomena. Another intriguing feature of the Forbidden Zone is its population of compact objects, such as neutron stars and stellar mass black holes. These remnants of massive stars are difficult to detect individually due to the dense stellar environment, but their collective gravitational effects influence the dynamics of the region. These objects are thought to form a dark cluster around Sagittarius A*, further contributing to the complexity of the central region. One of the most puzzling discoveries in the Forbidden Zone is the presence of young, massive stars in close proximity to Sagittarius A star. The conditions near the black hole are extremely hostile, with intense radiation and tidal forces that should prevent star formation. Yet, clusters of young stars, such as the Arches cluster and the Quintuplet cluster, exist in this environment. Their presence raises questions about how they formed. Did they form in situ, defying the odds? Or were they born farther away and later migrated inward? The galactic center is also a hotspot for high-energy phenomena. X-ray and gamma-ray emissions from the region reveal the presence of particles accelerated to near-light speeds. These emissions likely originate from interactions between magnetic fields, stellar winds, and the remnants of past supernovae. One notable source of high-energy radiation is the Fermi bubbles, two enormous, balloon-like structures extending above and below the galactic plane. These bubbles are thought to be the remnants of a powerful outburst from Sagittarius A*, millions of years ago, providing a glimpse into its more active past. Despite its hostility, the Forbidden Zone holds vital clues about the Milky Way's history and evolution. The dense concentration of stars and gas suggests that the galactic center has been a site of intense star formation in the past. Additionally, the interactions between Sagittarius A** and its surroundings offer insights into the behavior of supermassive black holes and their role in shaping galaxies. The study of the galactic center has been revolutionized by advancements in observational technology. Instruments like the Event Horizon Telescope, which captured the first image of a black hole shadow, and the Very Large Telescope VLT, which tracks the orbits of S-stars, have provided unprecedented detail about this region. Future missions, such as the European Extremely Large Telescope, ELT, and space-based observatories, promise to uncover even more about the Forbidden Zone's mysteries. Exploring the galactic center is not just a journey into the heart of the Milky Way, it is a quest to understand the extremes of physics. The region pushes the limits of our knowledge, challenging theories about gravity, star formation, and the behavior of matter in extreme conditions. It serves as a natural laboratory for testing the predictions of Einstein's theory of general relativity, particularly in the intense gravitational field of Sagittarius A star. The Forbidden Zone of the galactic center is a paradoxical place, a region of chaos and order, destruction and creation. It is both a graveyard of stars and a cradle of cosmic phenomena, shaping the Milky Way in profound ways. As we continue to study this enigmatic region, we not only deepen our understanding of the galaxy, but also gain a greater appreciation for the forces that govern the universe. The galactic warp. When we think of the Milky Way, the image that often comes to mind is a flat, elegant spiral galaxy with stars, gas, and dust arranged in a symmetrical disk. However, the reality is far more complex and intriguing. The Milky Way is not a perfectly flat structure. Its disk is warped and twisted, resembling a rippling wave rather than a smooth plane. This phenomenon, known as the galactic warp, has puzzled astronomers for decades, and its causes and consequences remain a subject of active research. The galactic warp is most evident in the outer regions of the Milky Way's disk. While the inner parts of the galaxy, where the spiral arms and most stars reside, are relatively flat, the outer disk begins to bend upward and downward, forming an S shape when viewed edge-on. This warp is subtle but significant, affecting the motion of stars and gas, and providing clues about the Milky Way's history and interactions with its cosmic environment. The discovery of the galactic warp dates back to observations of neutral hydrogen gas in the 1950s. Unlike stars, which are concentrated in the galaxy's brighter central regions, hydrogen gas extends far into the outer disk, making it an excellent tracer of the galaxy's shape. Radio telescopes revealed that the gas in these outer regions did not lie on a flat plane, but instead followed a warped pattern. Subsequent studies confirmed that stars in the outer disk also participate in this warp, though the effect is less pronounced than in the gas. One of the most pressing questions about the galactic warp is its origin. Several theories have been proposed, each highlighting different aspects of the galaxy's dynamics and interactions. One leading explanation involves the gravitational influence of the Milky Way's neighboring galaxies, particularly the Magellanic Clouds. These two irregular dwarf galaxies, the Large and Small Magellanic Clouds, are in a complex dance with the Milky Way, and their combined mass exerts a tidal pull on the outer disk. This gravitational tug could create oscillations in the disk, resulting in the observed warp. Another theory suggests that the warp is a relic of the Milky Way's past mergers with smaller galaxies. Over billions of years, the Milky Way has grown by accreting smaller galaxies, each adding its own stars, gas, and gravitational influence. These interactions can disturb the disk, creating ripples and warps that persist long after the merger. Evidence of such past interactions is seen in the form of stellar streams, remnants of disrupted galaxies that now orbit the Milky Way. The role of dark matter in shaping the galactic warp is also a topic of considerable interest. Dark matter, which forms a massive halo around the Milky Way, interacts gravitationally with the visible disk. If the dark matter halo is not perfectly symmetrical, as some models suggest, its uneven distribution could tilt and distort the disk, contributing to the warp. Understanding this connection could provide valuable insights into the nature and distribution of dark matter in the galaxy. The dynamics of the warp are as fascinating as its origins. Observations show that the warp is not static. It oscillates, with different parts of the disk moving at different rates. These oscillations are thought to arise from a combination of gravitational interactions, the galaxy's rotation, and the intrinsic motions of stars and gas. The warp's motion provides a unique opportunity to study the forces acting on the Milky Way and to test models of galactic dynamics. The galactic warp also has implications for the stars and gas in the outer disk. In these regions, the gravitational potential is weaker, making the motions of stars and gas more susceptible to perturbations. The warp can affect the orbits of stars, causing them to move in complex patterns that differ from the nearly circular orbits seen closer to the galactic center. These motions can influence the distribution of gas and the formation of new stars, shaping the evolution of the outer disk. Interestingly, the Milky Way is not the only galaxy with a warped disk. Observations of other spiral galaxies reveal that warps are a common feature, particularly in galaxies with extended gas disks. By studying these galaxies, astronomers can compare different warp patterns and identify the factors that contribute to their formation. These comparisons provide context for understanding the Milky Way's warp and its place in the broader cosmic landscape. One of the most intriguing aspects of the galactic warp is its connection to the Milky Way's future. The galaxy is on a collision course with the Andromeda Galaxy, and their eventual merger will profoundly reshape both systems. The gravitational forces during this interaction are expected to amplify the warp, creating new ripples and distortions in the disk. Studying the current warp can help astronomers predict the outcomes of this future event and understand the processes that govern galaxy mergers. The study of the galactic warp has been revolutionized by advances in observational technology. The Gaia mission, with its unprecedented ability to measure the positions and motions of stars, has provided detailed maps of the Milky Way structure, including the warp. By analyzing Gaia data, astronomers have identified subtle variations in the warp's shape and motion, offering new clues about its origins and dynamics. Meanwhile, radio telescopes like ALMA and the Square Kilometre Array are shedding light on the distribution of gas in the warped regions, revealing the interplay between stars, gas, and gravity. The galactic warp is a reminder of the dynamic and ever-changing nature of the universe. Far from being a static structure, the Milky Way is a living system, constantly shaped by internal forces and external interactions. The warp is a testament to the galaxy's resilience, a feature born of disruption, yet integrated into its elegant spiral form. As we continue to explore the galactic warp, we are uncovering not only the story of the Milky Way, but also the processes that govern galaxies across the cosmos. The warp is a window into the forces that shape the universe, a ripple in the fabric of the galaxy that speaks to the interconnectedness of all things. In studying its mysteries, we gain a deeper appreciation for the complexity and beauty of the Milky Way, a galaxy that, even in its imperfections, reveals the grandeur of the cosmos. The age of the Milky Way. The Milky Way, with its sprawling spiral arms and bustling star-filled regions, has long captivated humanity's imagination. But how old is this cosmic masterpiece? Determining the age of our galaxy is no small task. It involves piecing together clues from ancient stars, globular clusters, and the very fabric of the universe itself. Uncovering the age of the Milky Way is not just about understanding its history, but also about placing our galaxy in the broader timeline of the cosmos. The story begins with the birth of the universe, roughly 13.8 billion years ago, during the event known as the Big Bang. In its infancy, the universe was a hot, dense state composed mostly of hydrogen and helium. Over time, this material began to clump together under the force of gravity, forming the first stars and galaxies. The Milky Way was likely one of the early galaxies to emerge, assembling from smaller proto-galaxies through collisions and mergers. To estimate the Milky Way's age, astronomers turn to its oldest stars. Stars act as cosmic timekeepers, their lifespans and chemical compositions preserving a record of the conditions under which they formed. Among the most ancient stars are those found in globular clusters, densely packed groups of stars that orbit the galaxy's halo. These clusters are believed to have formed during the Milky Way's earliest stages, making them invaluable for age determination. By studying the light from stars and globular clusters, scientists can determine their ages with remarkable precision. The process involves analyzing the star's color and brightness, which are influenced by their mass and chemical composition. Using stellar evolution models, astronomers estimate that the oldest globular clusters in the Milky Way are around 12.5 to 13 billion years old, suggesting that the galaxy itself must be at least this old. Another key to the Milky Way's age lies in its metal-poor stars. In astronomy, metals refer to elements heavier than hydrogen and helium, which are produced through nuclear fusion in stars. The first stars in the universe contained almost no metals, as they formed from primordial gas left over from the Big Bang. Over time, successive generations of stars enriched the galaxy with heavier elements, seeding the interstellar medium with the building blocks for planets and life. Metal-poor stars, often found in the galactic halo, are relics of the Milky Way's formative years. These stars contain only trace amounts of metals, indicating that they formed before the galaxy had undergone significant chemical enrichment. By studying the chemical compositions of these ancient stars, astronomers can trace the timeline of the Milky Way's formation and evolution. One of the most famous examples of a metal-poor star is HD 140283, nicknamed the Methuselah star. Located relatively close to Earth, this star has an estimated age of 14 billion years, remarkably close to the age of the universe itself. While the exact age of HD 140283 is still debated, its extreme antiquity highlights the presence of stars that formed during the galaxy's earliest epochs. The Milky Way's age is also constrained by observations of its structure and dynamics. The galaxy's thin and thick disks, for example, provide insights into different stages of its formation. The thick disk, populated by older stars with lower metallicities, likely formed during the galaxy's turbulent youth, when mergers and interactions were common. In contrast, the thin disk, home to younger, metal-rich stars, represents a more recent phase of steady star formation. The halo, another critical component of the Milky Way, contains some of its oldest stars as well as remnants of ancient mergers with dwarf galaxies. These remnants, visible as streams of stars orbiting the galaxy, offer a glimpse into the Milky Way's early growth through accretion. By studying these stellar streams and their ages, astronomers can piece together the timeline of the galaxy's assembly. In addition to stars, the Milky Way's age is reflected in its dark matter halo. Dark matter, an invisible substance that makes up most of the galaxy's mass, plays a crucial role in its structure and evolution. Simulations of galaxy formation suggest that dark matter halos began forming shortly after the Big Bang, providing the scaffolding for galaxies like the Milky Way to assemble. The presence of an extensive dark matter halo around the Milky Way indicates that its roots extend back to the earliest epochs of cosmic history. Modern telescopes and space missions have revolutionized the study of the Milky Way's age. The Gaia mission, for example, has provided precise measurements of the positions and motions of billions of stars, enabling astronomers to map the galaxy's structure and trace its history. Similarly, spectroscopic surveys like Apogee and LAMOST have cataloged the chemical compositions of stars across the Milky Way, revealing patterns of enrichment that point to its age and formation. The quest to determine the Milky Way's age is not just about looking backward. It also provides a framework for understanding its future. The galaxy is still evolving, with ongoing star formation in regions like the spiral arms and interactions with neighboring galaxies like the Magellanic Clouds. These processes ensure that the Milky Way story is far from over, even as it approaches its next major chapter, a collision with the Andromeda Galaxy, predicted to occur in about 4.5 billion years. The age of the Milky Way also has profound implications for our understanding of life in the universe. By studying the timeline of star and planet formation in the galaxy, scientists can estimate when and where conditions for life might have arisen. The realization that Earth and its solar system are relative newcomers in a galaxy billions of years old raises questions about the potential for older, more advanced civilizations elsewhere in the Milky Way. Ultimately, the age of the Milky Way is a testament to the enduring creativity of the cosmos. From its chaotic beginnings as a collection of proto-galaxies to its current grandeur as a spiral galaxy, the Milky Way has been shaped by countless events over billions of years. Each star, nebula, and planet within it is a product of this ancient history, a reminder of the galaxy's journey through time. As we continue to explore the Milky Way, we are not only uncovering the story of our galaxy, but also connecting with a history that spans nearly the entire age of the universe. In understanding the Milky Way's age, we come closer to understanding our own place in the cosmos, a fleeting moment in the life of a galaxy that has witnessed the birth of stars, the formation of planets, and the emergence of life. Ghosts of collisions past. The Milky Way, vast and majestic as it appears, is not a solitary entity drifting serenely through the cosmos. Its history is one of dramatic encounters, cosmic collisions, and the remnants of long-vanished galaxies absorbed into its structure. These events, though ancient, have left lasting imprints, or ghosts, within the Milky Way. By studying these remnants, we uncover the tale of the galaxy's turbulent past and the cosmic forces that shaped it into what we see today. The Milky Way's growth, like that of most galaxies, has been fueled by mergers with smaller systems. These mergers are a fundamental part of galaxy formation in the universe, driven by the gravitational pull of massive structures. The smaller galaxies, known as dwarf galaxies, are drawn toward the Milky Way's immense gravity, eventually colliding and merging. In the process, their stars, gas, and dark matter are assimilated into the Milky Way, while their structures are stretched and distorted, leaving behind streams and halos of stellar debris. One of the most striking examples of these cosmic ghosts is the Sagittarius dwarf spheroidal galaxy. Discovered in the 1990s, this small galaxy is in the process of being torn apart by the Milky Way's gravity. Its stars have been pulled into long, looping streams that wrap around the galaxy, forming a visible halo of debris. These streams provide direct evidence of the ongoing merger and offer a window into the dynamics of such encounters. The Sagittarius stream is not the only remnant of a past collision. Other stellar streams crisscross the Milky Way's halo, each one a relic of a smaller galaxy or star cluster consumed in the distant past. These streams are like breadcrumbs, tracing the paths of ancient mergers and revealing the Milky Way's assembly history. By mapping these streams, astronomers can reconstruct the timeline of the galaxy's growth and identify the remnants of long-lost companions. One of the most significant discoveries in recent years is the Gaia Enceladus event. Using data from the Gaia mission, astronomers identified a population of stars in the Milky Way's halo with distinct chemical compositions and orbital patterns. These stars, which differ from the galaxy's native populations, are believed to have originated in a dwarf galaxy that merged with the Milky Way around 10 billion years ago. This event, named after the mythical figure Enceladus, reshaped the galaxy's structure, creating its thick disk and contributing a significant fraction of the stars in the halo. The impact of such collisions extends beyond the redistribution of stars. Mergers inject fresh material into the galaxy, fueling star formation and enriching the interstellar medium with new elements. The gravitational forces during these encounters can also trigger bursts of star formation, creating clusters of bright, young stars. In the case of the Gaia-Enceladus event, the influx of gas and stars likely played a key role in the Milky Way's early evolution. While these events have left behind visible traces, other mergers are less obvious. Some dwarf galaxies, like the Magellanic Clouds, are still in the early stages of interaction with the Milky Way. The large and small Magellanic Clouds, for example, are connected to the Milky Way by a stream of hydrogen gas known as the Magellanic Stream. This material, stripped from the clouds by tidal forces, is gradually falling into the Milky Way, where it will eventually contribute to star formation. The effects of collisions are not confined to the outer regions of the galaxy. Even the Milky Way's central regions bear the scars of past interactions. Observations of the galactic bulge and bar suggest that their formation was influenced by early mergers and the inflow of material from smaller systems. The bulge, in particular, contains stars with a wide range of ages and metallicities, reflecting the complex history of this region. The study of the Milky Way's collision history is not limited to visible stars and gas. Dark matter, the invisible yet dominant component of the galaxy, also plays a crucial role in mergers. When two galaxies collide, their dark matter halos interact gravitationally, influencing the distribution of stars and gas. Simulations of galaxy mergers, which include both visible and dark matter, provide insights into the dynamics of these events and their long-term effects on the galaxy's structure. One of the most fascinating aspects of studying galactic collisions is the realization that they are ongoing processes. While we often think of these events as belonging to the distant past, the Milky Way is still in the process of interacting with its neighbors. The Magellanic Clouds are gradually moving closer, and their eventual merger with the Milky Way will create new streams and bursts of star formation. Similarly, the Milky Way is on a collision course with the Andromeda Galaxy, a dramatic encounter that will reshape both galaxies over the next few billion years. The ghosts of past collisions also provide a cosmic perspective on the nature of galaxies. Far from being static structures, galaxies are dynamic systems that evolve through interactions and mergers. Each collision adds to the complexity of the galaxy, contributing stars, gas, and dark matter that are woven into its structure. This process, known as hierarchical growth, is a fundamental aspect of galaxy formation in the universe. The tools used to study these events have advanced significantly in recent decades. The Gaia mission, with its precise measurements of stellar positions and motions, has revolutionized our understanding of the Milky Way's structure and history. By analyzing the motions of stars in the halo, astronomers can identify streams and remnants of past mergers with unprecedented detail. Similarly, spectroscopic surveys like Apogee and SDSS provide chemical fingerprints of stars, revealing their origins and the conditions under which they formed. The study of the Milky Way's collision history is not just an exploration of the past. It also holds clues about the future. Understanding how galaxies grow and evolve through mergers helps astronomers predict the outcomes of future events, such as the Milky Way's impending collision with Andromeda. These predictions provide a glimpse into the distant future of our galaxy, offering a sense of continuity in the cosmic narrative. The ghosts of collisions past are a reminder of the Milky Way's dynamic nature. They tell a story of growth and transformation, a history written in the stars that surround us. As we study these remnants, we not only uncover the origins of our galaxy, but also gain a deeper appreciation for the forces that shape the universe. In their silent orbits, these cosmic ghosts speak of the Milky Way's journey, a journey marked by encounters, changes, and the enduring creativity of the cosmos. The dark matter enigma. The Milky Way, a luminous beacon of stars, gas, and dust, is not as it seems. Hidden in its vast expanse is a shadowy, invisible presence that dominates its mass and governs its structure: dark matter. This enigmatic substance, which neither emits nor absorbs light, is one of the greatest mysteries in modern astrophysics. Though unseen, its influence is profound, shaping the Milky Way and the universe itself. Unraveling the nature of dark matter is a quest that has captivated scientists and could redefine our understanding of the cosmos. The first hints of dark matter's existence emerged in the early 20th century, when astronomers noticed something peculiar about galaxies, including the Milky Way. Stars in the outer regions of galaxies were orbiting their centers much faster than expected based on the visible mass of stars and gas. According to Newtonian physics, these stars should have been flung into space, yet they remained bound to their galaxies. The only explanation was the presence of an unseen mass, a halo of dark matter enveloping the galaxies and providing the additional gravity needed to hold them together. In the Milky Way, the dark matter halo extends far beyond the visible disk, encompassing not only the spiral arms and the bulge but also the far reaches of the galactic halo. It is estimated that dark matter accounts for about 85% of the Milky Way's total mass, dwarfing the combined mass of its stars, planets, and gas. Without this dark matter, the galaxy would lack the gravitational glue to maintain its structure, and the stars within it would disperse into space. The precise nature of dark matter remains elusive. Unlike ordinary matter, which is composed of atoms, dark matter does not interact with electromagnetic radiation, making it invisible to telescopes. Its presence can only be inferred through its gravitational effects on visible matter, such as the motions of stars and gas, the bending of light from distant objects, gravitational lensing, and the behavior of galaxies and clusters. The leading candidates for dark matter are exotic particles that have yet to be directly detected. One prominent theory suggests that dark matter consists of WIMPs, weakly interacting massive particles, which interact only through gravity and possibly the weak nuclear force. Another hypothesis involves axions, lightweight particles that may solve puzzles in quantum physics while also explaining dark matter. These theoretical particles are the focus of numerous experiments on Earth and in space. Dark matter plays a crucial role in shaping the Milky Way structure. The halo of dark matter acts as a gravitational framework upon which the visible components of the galaxy are built. It influences the formation and dynamics of the galactic disk, the spiral arms, and the central bulge. Simulations of galaxy formation show that without dark matter, the Milky Way structure would be vastly different, perhaps more diffuse or irregular. The interactions between dark matter and visible matter are particularly evident in the motions of stars within the galactic halo. Stars in this region often exhibit orbits that are inconsistent with the visible mass of the galaxy, revealing the gravitational influence of dark matter. These motions are key to mapping the distribution of dark matter within the Milky Way, providing insights into its density and shape. The study of satellite galaxies around the Milky Way offers another avenue for understanding dark matter. Dwarf galaxies, such as the Magellanic Clouds and the Sagittarius Dwarf Galaxy, are embedded within the Milky Way's dark matter halo. Their orbits and interactions provide clues about the mass and extent of the halo. For instance, the tidal forces experienced by these satellites, forces that strip stars and gas from their outer regions, are influenced by the dark matter halo's gravity. One of the most intriguing aspects of dark matter is its role in the early universe. Simulations suggest that dark matter halos formed shortly after the Big Bang, providing the seeds for the growth of galaxies. These halos acted as gravitational wells, pulling in ordinary matter and creating the conditions for star formation. The Milky Way's dark matter halo likely began as one of these primordial structures, growing over billions of years through mergers and accretion. Dark matter is also a key player in the larger cosmic web. The Milky Way is part of a vast network of galaxies and dark matter filaments that crisscross the universe. These filaments connect clusters of galaxies, shaping the large-scale structure of the cosmos. The Milky Way's position within this web influences its motion and interactions, such as its impending collision with the Andromeda Galaxy. Efforts to detect dark matter directly are among the most ambitious endeavors in modern physics. Experiments like the Large Hadron Collider, as well as dedicated dark matter detectors buried deep underground, aim to capture elusive signals from dark matter particles. Space-based missions, such as the Fermi Gamma Ray Space Telescope, search for indirect evidence of dark matter annihilation or decay. While no definitive detections have been made, each experiment narrows the range of possibilities, bringing us closer to solving the mystery. The search for dark matter also extends to the Milky Way's halo, where some scientists speculate that dense clumps of dark matter could exist. These clumps, known as subhalos, might host their own dwarf galaxies or even influence the motions of stars in subtle ways. Identifying these subhalos could provide direct evidence of dark matter's distribution and properties. Despite the progress made, dark matter remains one of the most profound enigmas in astrophysics. Its existence challenges our understanding of the universe, pointing to physics beyond the standard model. It also raises philosophical questions about the nature of reality and the limitations of human perception. If dark matter comprises the majority of the universe's mass, then the cosmos we see is but a fraction of its true substance. The study of dark matter in the Milky Way is a testament to humanity's ingenuity and curiosity. By combining observations, simulations, and experiments, scientists are piecing together a picture of this invisible force that has shaped our galaxy and the universe. As we delve deeper into the dark matter enigma, we are not only exploring the mysteries of the cosmos, but also pushing the boundaries of human knowledge. Dark matter may be invisible, but its impact is undeniable. It binds the stars in the Milky Way, sculpts the galaxy's form, and guides its motion through the cosmic web. It is a silent force, present yet elusive, challenging us to uncover its secrets. In pursuing the nature of dark matter, we take one step closer to understanding the universe and our place within it. Peculiar objects in the galaxy. The Milky Way, a galaxy of spiraling stars and glowing nebulae, is more than a collection of predictable cosmic phenomena. Amid the familiar beauty lies a catalog of strange, mysterious, and downright peculiar objects. These oddities challenge our understanding of the universe, pushing the boundaries of physics and revealing the galaxy's untamed creativity. From rogue planets and hypervelocity stars to exotic stellar remnants and enigmatic cosmic structures, these peculiar objects add a sense of wonder to the Milky Way's intricate tapestry. One of the most intriguing classes of peculiar objects is rogue planets, worlds that drift freely through the galaxy, untethered to any star. Unlike traditional planets, which orbit stars, rogue planets are thought to form within planetary systems before being ejected by gravitational interactions or violent events such as stellar explosions. These dark wanderers are nearly invisible, detectable only through their gravitational effects or fleeting events like microlensing, where their gravity bends the light of a distant star. Rogue planets could number in the billions, far exceeding the number of stars in the Milky Way. Some may harbor conditions capable of sustaining life, with internal heat from radioactive decay or tidal forces providing warmth even in the absence of sunlight. The discovery of rogue planets raises profound questions about the diversity of planetary environments and the potential for life in the galaxy's darker corners. Another class of peculiar objects is hypervelocity stars. Stars traveling at extraordinary speeds, often exceeding the escape velocity of the Milky Way. These cosmic outliers are typically flung out of the galactic center, where interactions with the supermassive black hole, Sagittarius A*, can accelerate stars to breathtaking velocities. Some hypervelocity stars may originate from binary systems, where one star is ejected while its companion is consumed by the black hole. Hypervelocity stars are rare but fascinating, offering insights into the dynamics of the galactic center and the gravitational power of black holes. Their trajectories provide valuable information about the shape and extent of the Milky Way's dark matter halo, as their motion is influenced by the galaxy's unseen mass. Among the most bizarre objects in the galaxy are magnetars, a type of neutron star with magnetic fields so intense that they defy comprehension. These fields, 1 trillion times stronger than Earth's, can warp the fabric of space-time and emit bursts of high-energy radiation. Magnetars are born from massive stars that collapse in supernovae, leaving behind ultra-dense cores. Unlike ordinary neutron stars, magnetars undergo violent outbursts, releasing X-rays and gamma rays in sudden, powerful flares. Magnetars are also linked to the mysterious phenomena of fast radio bursts, FRBs, short, intense bursts of radio waves originating from distant galaxies. While most FRBs come from outside the Milky Way, some have been traced to magnetars within our galaxy. These discoveries suggest that magnetars may hold the key to understanding these enigmatic cosmic signals. The Milky Way is also home to peculiar planetary systems that defy the norms observed in our solar system. Some stars host hot Jupiters, gas giants that orbit perilously close to their parent stars, completing an orbit in days or even hours. Others have tightly packed systems of rocky planets, with orbits so close that gravitational interactions lead to chaotic dynamics. There are also binary systems where one star's gravity has stripped material from its companion, creating a cosmic tug-of-war. One particularly strange discovery is the class of planets orbiting pulsars, rapidly spinning neutron stars that emit beams of electromagnetic radiation. These planets, such as those in the system of PSRB 1257+12, exist in environments bathed in intense radiation, making them some of the least hospitable worlds imaginable. Their very existence challenges theories of planet formation, as pulsar planets are thought to form from the remnants of supernova explosions. In addition to peculiar stars and planets, the Milky Way contains cosmic voids and bubbles, such as the local bubble, a region of space surrounding the solar system that is relatively devoid of interstellar gas. This cavity, created by ancient supernovae, stretches hundreds of light years and influences the movement of stars and interstellar material. Similar structures, such as the Fermi bubbles extending from the galactic center, reveal the dynamic processes that shape the galaxy over millions of years. The galactic center itself is a hotbed of peculiar phenomena. Beyond the presence of Sagittarius A*, the region is home to mysterious entities known as G-objects, which exhibit characteristics of both stars and gas clouds. These objects are stretched and distorted as they approach the supermassive black hole, raising questions about their nature and origin. Are they young stars enveloped in thick gas, or entirely new types of objects born in the galaxy's most extreme environment? Another peculiar find in the galactic center is the presence of Peony Nebula star, one of the most luminous stars in the Milky Way. Its intense brightness, combined with its location in a dense and chaotic region, challenges theories of star formation and stability. Similarly, the discovery of young stars near Sagittarius A*, in a region hostile to star formation, has puzzled astronomers for decades. The peculiarities of the Milky Way are not limited to individual objects. Entire structures defy explanation. The stellar stream of the Orphan and other remnants of galactic mergers form faint trails of stars that arc across the sky. These streams, visible only through meticulous analysis of star motions, are the leftover debris of dwarf galaxies torn apart by the Milky Way's gravity. Even more enigmatic are the ultra-diffuse galaxies within the Milky Way's halo. These faint, ghostly galaxies have the mass of small galaxies, but are spread out over vast areas, making them incredibly dim. Their survival in the presence of the Milky Way's gravitational pull raises questions about the role of dark matter in holding them together. The study of peculiar objects in the Milky Way is a frontier of astrophysics, blending curiosity and cutting-edge science. Each discovery, whether it's a rogue planet, a hypervelocity star, or a magnetar, expands our understanding of what is possible in the universe. These objects challenge existing theories, inspire new questions, and remind us that the cosmos is far more diverse and dynamic than we can imagine. As we explore these peculiarities, we not only uncover the Milky Way's secrets, but also gain a deeper appreciation for the boundless creativity of the universe. These oddities are not outliers. They are testaments to the complexity and wonder of a galaxy that continues to surprise and inspire. The peculiar objects of the Milky Way are its exclamation points, emphasizing the marvels hidden within its vast expanse. The future of the Milky Way. The Milky Way, a galaxy alive with the light of billions of stars, is far from static. It is a dynamic system, constantly evolving under the influence of gravity, stellar activity, and cosmic interactions. As we gaze upon its spiraling arms and radiant core, we must also wonder, what does the future hold for our galactic home? Will it maintain its majestic form, or will it transform into something entirely new? To answer these questions, astronomers rely on simulations, observations, and the laws of physics to predict the Milky Way's long-term destiny. The current state of the Milky Way. Before envisioning the Milky Way's future, it is essential to understand its present state. The galaxy spans approximately 100,000 light-years and contains hundreds of billions of stars, along with vast amounts of gas, dust, and dark matter. Its spiral structure, sustained by density waves, drives star formation in its arms, while the central bar and bulge harbor ancient stars and a supermassive black hole, Sagittarius A star. The galaxy is surrounded by a massive halo of dark matter that extends far beyond its visible components, influencing its motion and interactions with nearby galaxies. Within this halo are satellite galaxies, such as the Magellanic Clouds and dozens of dwarf galaxies, many of which are slowly merging with the Milky Way. These mergers are critical to understanding the galaxy's ongoing evolution. The collision with Andromeda. The most dramatic event in the Milky Way's future is its impending collision with the Andromeda Galaxy, currently located about 2.5 million light-years away. Andromeda, another spiral galaxy and the largest member of the Local Group, is moving toward the Milky Way at a speed of about 110 kilometers per second. This cosmic rendezvous is expected to occur in approximately 4.5 billion years. When the Milky Way and Andromeda collide, their stars, gas, and dark matter will interact, creating tidal forces that stretch and distort their shapes. Despite the term collision, the vast distances between stars make direct impacts unlikely. Instead, the galaxies will pass through each other, triggering bursts of star formation as gas clouds compress and mix. Over time, their orbits will decay, leading to a full merger. The result of this galactic dance will be a new entity, often referred to as Milkomeda or the Milky-Drameda galaxy. This new galaxy is expected to have an elliptical or lenticular shape, with little resemblance to the spirals we see today. The merger will erase the distinct identities of both galaxies, blending their stars, gas, and dark matter into a unified structure. The fate of the solar system. As the Milky Way transforms through its collision with Andromeda, the solar system's fate hangs in the balance. Current simulations suggest that the Sun and its planets are unlikely to collide with other stars directly. However, the gravitational upheaval could eject the solar system from its current orbit, flinging it into a distant region of the merged galaxy, or even into intergalactic space. Regardless of its final position, the solar system will witness profound changes in its cosmic neighborhood. By the time the merger occurs, the Sun will have evolved into a red giant, nearing the end of its life. Its outer layers will expand, engulfing the inner planets, including Earth. Eventually, the Sun will shed its outer layers entirely, leaving behind a white dwarf. This transformation, coupled with the galaxy's larger changes, ensures that the solar system's future will look vastly different from its present. Star formation in the distant future. The merger with Andromeda is not the end of the story. In the aftermath, the gas and dust from both galaxies will fuel a final wave of star formation, creating new stellar populations. However, this activity will eventually wane as the available gas is depleted. Without fresh material to sustain it, star formation will slow to a trickle, and the galaxy will transition into a quieter, less active phase. Over billions of years, the brightest stars will burn out, leaving behind long-lived red dwarfs, white dwarfs, neutron stars, and black holes. The galaxy will grow dimmer, its remaining stars slowly fading into darkness. The role of dark matter. Dark matter, which forms the structural backbone of the Milky Way, will continue to influence the galaxy's evolution. It will help stabilize the merged Milkomeda galaxy, ensuring its shape and structure persist for billions of years. However, dark matter's interactions with ordinary matter are purely gravitational, meaning it will not reignite star formation or reverse the galaxy's decline. The study of dark matter also raises questions about the Milky Way's interactions with its broader cosmic environment. Over time, The local group will coalesce into a single gravitationally bound system, dominated by Milky Way. This structure will eventually separate from other galaxy clusters as the universe continues to expand at an accelerating rate. The ultimate endgame. As time stretches into the distant future, trillions of years from now, the Milky Way, Andromeda, and the rest of the local group will become isolated from the broader universe due to cosmic expansion. This phenomenon, driven by dark energy, will pull distant galaxies out of view, leaving Milky Way as an island in an increasingly empty cosmos. Within Milky Way, the remaining stars will slowly fade, and stellar remnants will dominate the galaxy. The occasional merger of black holes will produce bursts of energy, but the galaxy itself will grow increasingly cold and dark. Eventually, the galaxy will consist mostly of black holes, white dwarfs, and dark matter, a cosmic graveyard of sorts. On even longer timescales, approaching the heat death of the universe, the Milky Way's remnants will decay further. Black holes may evaporate through Hawking radiation, and all remaining matter could disperse into a thin, featureless soup of subatomic particles. The universe itself will become a vast, cold expanse of emptiness, devoid of structure and activity. A reflection on the Milky Way's legacy. The future of the Milky Way, though marked by dramatic transformations and eventual decline, is also a testament to the galaxy's resilience and complexity. Over billions of years, it has grown from a collection of primordial gas clouds into a sprawling spiral galaxy, nurturing countless stars, planets, and potentially life. Its story is one of constant change, shaped by the interplay of gravity, matter, and time. While the Milky Way's future may seem distant and abstract, it serves as a reminder of the impermanence of cosmic structures and the vast timescales on which the universe operates. As we study the galaxy and its evolution, we gain not only scientific knowledge, but also a sense of connection to a larger narrative, one that stretches from the earliest moments of the cosmos to its farthest reaches. The Milky Way's journey is far from over. Its transformations, collisions, and eventual fading are all part of the ongoing story of the universe, a story that continues to inspire awe and curiosity as we look to the stars. The role of supernovae. Among the most spectacular and transformative events in the universe, supernovae are cosmic explosions that release unimaginable energy, outshining entire galaxies for brief moments. Yet, their significance extends far beyond their dazzling displays. Supernovae are agents of change and renewal, shaping the Milky Way and influencing the evolution of stars, planets, and even life. These explosive events play a central role in the galaxy's life cycle, driving chemical enrichment, star formation, and the dynamics of the interstellar medium. What are supernovae? Supernovae occur when stars reach the end of their lives, but the exact mechanisms depend on the type of star involved. Broadly, there are two main types of supernovae. 1. Core collapse supernovae. These occur in massive stars, typically more than 8 times the mass of the Sun. After exhausting their nuclear fuel, these stars can no longer support themselves against gravity. Their cores collapse, triggering a shockwave that expels the outer layers of the star in a brilliant explosion. The remnants may become neutron stars or black holes. 2. Type Ia supernovae. These involve white dwarfs and binary systems. If a white dwarf accretes enough material from its companion star to exceed the Chandrasekhar limit, about 1.4 times the mass of the Sun, it undergoes a thermonuclear explosion, completely destroying the star. These explosions are consistent in their brightness, making them essential tools for measuring cosmic distances. Supernovae as chemical enrichers. Supernovae are the universe's master chemists, forging and dispersing heavy elements into the galaxy. During their lifetimes, stars create lighter elements like carbon, oxygen, and nitrogen through nuclear fusion. In their final moments, supernovae generate heavier elements such as iron, gold, and uranium, processes that occur during the explosion or through neutron capture in the ensuing shockwaves. These newly formed elements are ejected into the interstellar medium, enriching the gas and dust that will form the next generation of stars and planets. Without supernovae, the Milky Way would lack the diversity of elements needed for rocky planets, oceans, and even life. The very atoms in your body, calcium in your bones, iron in your blood, and carbon in your DNA, were forged in the cores of stars and distributed by supernovae billions of years ago, shaping the interstellar medium. Supernovae have a profound impact on the interstellar medium, the vast expanse of gas and dust that fills the Milky Way. When a supernova explodes, it sends shock waves through its surroundings, compressing gas and creating turbulence. These shock waves can trigger the collapse of nearby gas clouds, initiating the formation of new stars. This process, known as triggered star formation, ensures that supernovae contribute to the galaxy's cycle of creation and destruction. At the same time, supernovae can clear out regions of the interstellar medium, creating vast cavities known as supernova remnants. These remnants, such as the Crab Nebula and the Veil Nebula, are some of the most beautiful and dynamic structures in the galaxy. They serve as laboratories for studying the interplay of high-energy particles, magnetic fields, and shock waves, driving galactic evolution. The combined effects of many supernovae shape the larger structure of the Milky Way. In regions of intense star formation, such as the spiral arms, the frequent explosions of massive stars inject energy into the surrounding environment. This energy drives galactic winds, powerful outflows of gas that extend far beyond the galaxy's disk. These winds regulate star formation by removing gas from the galaxy, preventing runaway starburst activity. Supernovae also contribute to the formation of larger galactic structures, such as bubbles and superbubbles. These features are created when multiple supernovae explode in close proximity, forming expanding shells of hot, ionized gas. Over time, these bubbles can merge, creating enormous cavities like the local bubble, a region of low-density gas surrounding the solar system, illuminating the universe. Type Ia supernovae, with their predictable brightness, have become critical tools for understanding the cosmos. By comparing the observed brightness of these explosions to their intrinsic luminosity, astronomers can calculate their distances. This method, known as the standard candle technique, was instrumental in discovering the accelerating expansion of the universe and the existence of dark energy. Core collapse supernovae, meanwhile, provide insights into the life cycles of massive stars and the mechanisms of stellar death. Observations of nearby supernovae, such as SN 1987A in the Large Magellanic Cloud, have revealed details about the dynamics of these explosions, the formation of neutron stars, and the production of heavy elements. Supernovae and the origins of life. The connection between supernovae and life is profound. By distributing elements like carbon, oxygen, and nitrogen, supernovae create the chemical conditions necessary for life to arise. However, their influence is not always beneficial. The intense radiation and high-energy particles produced by supernovae, known as cosmic rays, can impact planetary atmospheres and ecosystems. Some studies suggest that nearby supernovae could have influenced Earth's biological history. For instance, high levels of cosmic rays might trigger climate changes or even mass extinctions by depleting the ozone layer. Conversely, the elements distributed by supernovae are essential for building planets and the molecules of life, highlighting the dual role of these explosions as both creators and disruptors. Observing supernovae in the Milky Way. Supernovae are rare events in a galaxy like the Milky Way, occurring roughly once every 50 years. However, their remnants persist for thousands of years, offering a wealth of observational data. Radio, X-ray, and gamma-ray telescopes allow astronomers to study supernova remnants in detail, revealing the complex interplay of particles, fields, and shock waves. One of the most famous supernova remnants is the Crab Nebula, the result of a supernova observed by Chinese astronomers in 1054 CE. This remnant contains a pulsar at its center, emitting beams of radiation that illuminate the surrounding nebula. Another example is the Valus supernova remnant, a vast structure visible in multiple wavelengths, showcasing the intricate interactions between the explosion's debris and the interstellar medium. The future of supernova studies. The next galactic supernova is eagerly anticipated, as it will provide an unprecedented opportunity to study these events up close. Advances in technology, such as the Vera C. Rubin Observatory and the James Webb Space Telescope, promise to revolutionize our understanding of supernovae, from their precursors to their long-term effects on the galaxy. In addition, Theoretical models and simulations are helping scientists explore the physics of supernovae in greater detail. These efforts aim to answer fundamental questions, such as how core collapse supernovae produce neutron stars and black holes, and the role of neutrinos in driving these explosions. A galactic legacy, supernovae are more than fleeting spectacles. They are vital to the Milky Way's evolution. These explosions enrich the galaxy with heavy elements, trigger the formation of new stars, and shape the interstellar medium. They are the architects of cosmic transformation, ensuring that the galaxy remains a dynamic and evolving system. As we study supernovae, we uncover the interconnectedness of the cosmos, a universe where the death of one star sows the seeds for new beginnings. In their brilliance, supernovae illuminate not just the galaxy, but also the profound processes that drive the cycles of creation and renewal in the universe. The Milky Way's magnetic field. Invisible but pervasive, the magnetic field of the Milky Way is a fundamental yet mysterious aspect of our galaxy. Like an unseen web of energy, it threads through the interstellar medium, influencing the motion of charged particles, the formation of stars, and the dynamics of gas and dust. Though it cannot be observed directly, the magnetic field leaves its fingerprints across the galaxy, shaping its evolution and revealing the hidden forces at work within the cosmos. What is a galactic magnetic field? A magnetic field is created by the movement of electrically charged particles. In the Milky Way, this field is generated by the turbulent motions of ionized gas in the galactic disk. These motions, combined with the galaxy's rotation, give rise to a dynamo effect, amplifying and sustaining the magnetic field over billions of years. The Milky Way's magnetic field is a large-scale structure that extends across the entire galaxy, but it also has local variations on smaller scales. It is a composite of an ordered component, aligned with the spiral arms, and a chaotic, turbulent component that fluctuates randomly. Together, these components create a complex and dynamic system that interacts with the galaxy's stars, gas, and cosmic rays. How do we measure the magnetic field? Since magnetic fields are invisible, astronomers rely on indirect methods to measure them. One of the most effective techniques involves the polarization of light. When light from stars or other sources passes through interstellar dust grains, which tend to align with the magnetic field, it becomes polarized. By analyzing the polarization of starlight, astronomers can infer the direction and strength of the magnetic field along the line of sight. Another key method is Faraday rotation, which occurs when polarized radio waves pass through a magnetized plasma. The magnetic field causes the plane of polarization to rotate, with the amount of rotation depending on the field's strength and the density of electrons in the plasma. By studying Faraday rotation in pulsar signals or distant radio sources, astronomers can map the magnetic field in different regions of the galaxy. Observations of synchrotron radiation, emitted by relativistic electrons spiraling around magnetic field lines, also provide valuable information. This radiation, seen in radio wavelengths, reveals the structure and strength of the magnetic field in regions where cosmic rays interact with the interstellar medium. The structure of the Milky Way's magnetic field. The large-scale magnetic field of the Milky Way is thought to follow the spiral pattern of the galaxy's arms. This alignment suggests that the field is tightly coupled with the interstellar medium, influencing the motion of gas and dust and being shaped by the same processes that govern the galaxy's structure. The field is strongest in the galactic plane, where the density of gas and stars is highest. However, it also extends into the halo, where it becomes more diffuse and chaotic. In the central regions of the galaxy, near the supermassive black hole, Sagittarius A*, the magnetic field becomes more intense and complex, interacting with the high-energy environment of the galactic core. On smaller scales, the magnetic field exhibits a tangled, turbulent structure, driven by the motions of gas and the shockwaves from supernovae. These local variations play a critical role in regulating star formation and shaping the morphology of molecular clouds, the birthplaces of stars. The role of the magnetic field in star formation. The magnetic field is a key player in the process of star formation. Within molecular clouds, the interplay between gravity, turbulence, and magnetic forces determines whether a cloud will collapse to form stars or remain stable. The magnetic field can provide support against gravitational collapse by counteracting the inward pull of gravity, particularly in diffuse regions. However, in dense regions where star formation occurs, the magnetic field can be weakened by turbulence or dissipated through processes like ambipolar diffusion, allowing the gas to collapse. The alignment of magnetic field lines with the shapes of molecular clouds, observed in regions like the Orion Nebula, suggests that the field also influences the direction and efficiency of star formation. Once stars form, their winds and radiation interact with the magnetic field, reshaping it and injecting energy into the surrounding medium. Supernova explosions, in particular, create shock waves that compress and tangle the magnetic field, contributing to its complexity and driving turbulence in the interstellar medium. Magnetic fields and cosmic rays. The Milky Way's magnetic field is a critical factor in the propagation of cosmic rays. High-energy particles originating from supernovae, active galactic nuclei, and other energetic phenomena. As cosmic rays travel through the galaxy, they spiral along magnetic field lines, following paths that can be deflected and scattered by turbulence. This interaction not only influences the distribution of cosmic rays, but also affects the heating and ionization of the interstellar medium. Cosmic rays play a significant role in driving chemical reactions in dense clouds, contributing to the formation of complex molecules, including those that are precursors to life. The galactic center's magnetic mysteries. The central regions of the Milky Way, near Sagittarius A*, present some of the most intriguing magnetic phenomena in the galaxy. Observations reveal intense magnetic fields that are highly ordered and perpendicular to the galactic plane. These fields may help channel gas into the central black hole or influence the dynamics of high-energy particles in this extreme environment. One of the most striking features in the galactic center is the presence of non-thermal radiofilaments, long, narrow structures aligned with the magnetic field. These filaments, some stretching for tens of light years, are unique to the galactic center and offer clues about the interaction between magnetic fields, cosmic rays, and the turbulent gas in this region. Magnetic fields beyond the Milky Way. The study of the Milky Way's magnetic field is part of a broader effort to understand magnetic fields in galaxies across the universe. Observations of external galaxies reveal a wide variety of magnetic structures, from ordered fields in spiral galaxies to chaotic fields in irregular systems. Comparing the Milky Way's field to those in other galaxies helps astronomers identify universal patterns and processes, shedding light on the origins and evolution of galactic magnetism. The challenges of understanding galactic magnetism. Despite significant progress, many questions about the Milky Way's magnetic field remain unanswered. How did the field originate, and how has it evolved over billions of years? What role does the dynamo effect play in sustaining the field, and how does it interact with other galactic processes? Addressing these questions requires advances in both observations and theory, as well as the development of more sophisticated simulations. The future of magnetic field studies. Future missions and telescopes promise to revolutionize our understanding of the Milky Way's magnetic field. Instruments like the Square Kilometre Array, SKA, will provide unprecedented sensitivity to radio emissions, allowing astronomers to map the magnetic field in exquisite detail. These observations, combined with data from infrared and X-ray telescopes, will offer a more comprehensive view of the field's structure and interactions. Simulations, powered by next-generation supercomputers, will also play a crucial role in unraveling the complexities of magnetic fields. By modeling the interplay between gravity, turbulence, and magnetic forces, scientists can explore scenarios for the field's origin and evolution, as well as its impact on the galaxy. The invisible thread of the Milky Way. The magnetic field of the Milky Way is a silent force, invisible yet essential to the galaxy's dynamics. It shapes the interstellar medium, guides the motion of cosmic rays, and influences the formation of stars and planets. As we study this enigmatic force, we uncover a deeper understanding of the interconnected processes that govern the galaxy, revealing the hidden threads that weave the Milky Way's intricate design. Interstellar medium mysteries. The interstellar medium, ISM, the vast expanse of gas, dust, and cosmic rays that fills the space between stars, is far from empty. This seemingly ethereal substance is the lifeblood of the Milky Way, driving star formation, hosting complex chemistry, and acting as the stage for countless cosmic processes. Yet, for all its importance, the ISM remains one of the galaxy's most enigmatic components. Its dynamic nature, diverse phases, and role in the Milky Way's evolution make it a focus of both fascination and inquiry. What is the interstellar medium? The ISM consists primarily of hydrogen and helium, the most abundant elements in the universe, along with trace amounts of heavier elements and dust particles. Despite its apparent sparsity, on average, there is only about 1 atom per cubic centimeter. It accounts for roughly 10 to 15% of the visible mass of the Milky Way. Distributed unevenly across the galaxy, the ISM forms intricate structures, from dense molecular clouds to vast, diffuse regions of hot gas. The ISM is not a uniform substance, but is divided into distinct phases based on temperature, density, and ionization. Molecular gas, the coldest and densest phase, where temperatures dip to just a few degrees above absolute zero. This phase is found in molecular clouds, the nurseries of star formation, where hydrogen exists in its molecular form, H2. Neutral atomic gas, a slightly warmer phase, with temperatures of a few hundred Kelvin. This phase is composed of neutral hydrogen, Hi, and forms extensive regions within the galactic disk. Ionized gas, found in regions where high-energy radiation from stars ionizes hydrogen, Hi regions. These areas are often associated with young, massive stars. Warm ionized medium, WIM, a diffuse, extended phase of ionized gas with temperatures of 10,000 Kelvin. Hot ionized medium, HIM, the rarefied, high-temperature phase, millions of Kelvin, that fills cavities created by supernova explosions and stellar winds. These phases coexist and interact, creating a dynamic and ever-changing environment that is both a product of and a participant in the galaxy's evolution. The role of the ISM in star formation. One of the most critical functions of the ISM is its role in star formation. Stars are born in the densest regions of molecular clouds, where gravity overcomes thermal pressure, causing the gas to collapse. These clouds are often shaped and triggered by external forces, such as shock waves from supernovae or the motion of spiral arms compressing gas as they rotate. The ISM's composition is crucial for the star formation process. Dust grains, though making up only about 1% of the ISM by mass, act as catalysts for molecular hydrogen formation and as shields against radiation, allowing gas to cool and condense. These grains also harbor complex chemistry, leading to the formation of organic molecules that may serve as precursors to life. However, not all regions of the ISM are conducive to star formation. The presence of turbulence, magnetic fields, and cosmic rays can inhibit the collapse of gas, creating a delicate balance between star-forming and quiescent regions. Understanding this interplay remains a major challenge in astrophysics. Chemical mysteries of the ISM. The ISM is a cauldron of chemical activity, where atoms and molecules combine to form some of the most complex compounds found in nature. Observations of molecular clouds have revealed a rich inventory of molecules, including water, ammonia, and carbon monoxide, as well as more complex organic molecules like formaldehyde and methanol. The discovery of polycyclic aromatic hydrocarbons, PAHs, large organic molecules thought to be precursors to life, highlights the ISM's potential role in the chemical evolution of the galaxy. Despite these discoveries, many mysteries remain. How do complex molecules form in the harsh conditions of space? What processes govern the abundance and distribution of these molecules? And what role does the ISM play in delivering these compounds to forming planetary systems? Answering these questions could shed light on the origins of life and the chemical pathways that connect stars, planets, and living organisms. The dynamics of the ISM. The ISM is a highly dynamic environment, shaped by the interplay of gravity, magnetic fields, turbulence, and stellar feedback. Stellar winds, supernova explosions, and radiation pressure inject energy into the ISM, driving turbulence and creating shockwaves that propagate through the medium. These processes create structures such as bubbles, filaments, and shells, which can span hundreds of light years. One of the most striking features of the ISM is its ability to form vast cavities, such as the local bubble, a region of low-density gas surrounding the solar system. This bubble, created by ancient supernovae, interacts with neighboring bubbles and the larger structures of the galaxy, influencing the distribution of gas and the flow of cosmic rays. The ISM also plays a role in the propagation of galactic winds, outflows of gas driven by star formation and supernovae. These winds regulate the galaxy's gas content, preventing runaway star formation and recycling material into the galactic halo. The interaction between the ISM and these winds is critical for understanding the Milky Way's evolution. Observing the ISM. Studying the ISM requires observations across the electromagnetic spectrum, as its diverse phases emit and absorb light at different wavelengths. Radio telescopes are essential for mapping neutral hydrogen, HI, and molecular gas, while infrared observations reveal the distribution of dust and complex molecules. X-ray telescopes, such as Chandra and XMM Newton, probe the hot ionized medium, providing insights into supernova remnants and galactic bubbles. Advances in technology have allowed astronomers to create detailed maps of the ISM, revealing its intricate structure and uncovering previously unseen phenomena. For example, the Planck satellite's observations of polarized light have provided new insights into the alignment of dust grains with the galactic magnetic field, offering clues about the field's structure and strength. The ISM and the galactic ecosystem. The ISM is not an isolated component of the Milky Way, but a vital part of its ecosystem. It acts as a reservoir of material for star formation, a medium for the propagation of cosmic rays, and a site for chemical reactions that shape the galaxy's composition. Its interactions with stars, supernovae, and the magnetic field ensure that it remains dynamic and ever-changing. The ISM also serves as a bridge between generations of stars. The material expelled by dying stars enriches the ISM with heavy elements, which are then incorporated into new stars and planets. This cycle of enrichment and renewal is fundamental to the galaxy's evolution and the diversity of its stellar populations. Unanswered questions and future research. Despite significant progress, the ISM remains a source of profound mysteries. How do molecular clouds form and evolve? What governs the transition between the different phases of the ISM? And how do galactic scale processes, such as interactions with neighboring galaxies, influence the ISM's structure and dynamics? Future observatories, such as the Square Kilometre Array, SK, and the James Webb Space Telescope, JWST, promise to revolutionize our understanding of the ISM. These instruments will provide unprecedented sensitivity and resolution, allowing astronomers to study the ISM's smallest structures and its largest scale interactions. The hidden heart of the galaxy. The interstellar medium is the hidden heart of the Milky Way, a dynamic and complex environment that sustains the galaxy's life cycle. It is the birthplace of stars, the canvas for cosmic chemistry, and the arena for powerful interactions that shape the galaxy's structure. As we explore its mysteries, we uncover not only the processes that govern the Milky Way, but also the fundamental forces that drive the evolution of galaxies across the universe. The galactic outskirts. The Milky Way's outskirts, often overlooked in favor of its bustling spiral arms and luminous core, are a realm of intrigue and subtle beauty. These far-flung regions, stretching tens of thousands of light-years beyond the visible disk, represent the galaxy's frontier. Sparse and enigmatic, the outskirts harbor stellar streams, dark matter, gas clouds, and ancient stars that hold clues to the Milky Way's history, structure, and interactions with the larger cosmos. What defines the galactic outskirts? The outskirts of the Milky Way encompass the regions beyond its well-defined spiral disk, including the stellar halo, the dark matter halo, and the distant gas reservoirs that extend far from the galactic plane. Unlike the dense and bright inner regions, the outskirts are diffuse and faint, populated by scattered stars, globular clusters, and tenuous gas. While the boundaries of the outskirts are not sharply defined, they extend hundreds of thousands of light-years from the galactic center. The edge of the visible disk, often marked by a steep drop in the density of stars and gas, is typically placed at around 50,000 to 60,000 light-years. Beyond this lies the stellar halo, which stretches to at least 300,000 light-years and contains some of the galaxy's most ancient stars. The stellar halo, a relic of the past. The stellar halo is a sparsely populated region dominated by old, metal-poor stars that formed in the early stages of the Milky Way's assembly. These stars are distributed in a roughly spherical shape, orbiting the galactic center on eccentric and randomly oriented paths. Unlike the organized rotation of stars in the disk, the stars in the halo exhibit chaotic motions, reflecting their origins in the galaxy's tumultuous past. The halo is also home to numerous globular clusters, dense collections of stars that are among the oldest objects in the galaxy. These clusters act as time capsules, preserving the conditions of the early universe. By studying their ages, chemical compositions, and orbits, astronomers can reconstruct the events that shaped the Milky Way, including mergers with smaller galaxies. Stellar streams, traces of galactic cannibalism. One of the most fascinating features of the galactic outskirts is the presence of stellar streams, elongated trails of stars that arc across the sky. These streams are the remnants of dwarf galaxies and globular clusters that were disrupted and torn apart by the Milky Way's gravity. Their stars, stripped from their original systems, now orbit the galaxy as part of the stellar halo. The Sagittarius stream is one of the most prominent examples, originating from the ongoing merger of the Sagittarius dwarf spheroidal galaxy with the Milky Way. This stream, which wraps around the galaxy in multiple loops, provides a vivid record of the interaction and reveals the gravitational influence of the Milky Way's dark matter halo. Other streams, such as the Orphan stream and the GD1 stream, offer additional evidence of past mergers. By mapping these streams and analyzing the motions of their stars, astronomers can probe the distribution of dark matter in the Milky Way and gain insights into the galaxy's hierarchical growth. Dark matter halo, the invisible giant. The outskirts of the Milky Way are dominated by the dark matter halo, an enormous, invisible structure that extends far beyond the stellar halo. This halo, which contains the majority of the galaxy's mass, acts as a gravitational scaffold, holding the visible galaxy together and influencing the orbits of stars, gas, and satellite galaxies. Dark matter's presence in the outskirts is inferred from the motions of stars and satellite galaxies, which move faster than expected based on visible matter alone. Understanding the distribution and properties of the dark matter halo is one of the central goals of modern astrophysics, as it holds clues to the nature of dark matter and its role in galaxy formation. Recent studies suggest that the dark matter halo may not be perfectly spherical, but instead exhibit distortions or asymmetries caused by interactions with other galaxies, such as the Magellanic Clouds. These interactions may also create substructures within the halo, such as clumps of dark matter that can influence the motions of stars and streams. Gas in the galactic outskirts. The outskirts of the Milky Way are not devoid of gas. The circumgalactic medium, CGM, is a diffuse and ionized halo of gas that surrounds the galaxy, extending to distances of several 100,000 light-years. This gas, enriched with metals from supernova explosions, serves as a reservoir for future star formation and plays a critical role in the galaxy's evolution. The CGM is fed by inflows of pristine gas from the cosmic web and outflows driven by galactic winds. Observations of the CGM using ultraviolet and X-ray telescopes have revealed a complex and dynamic environment, with evidence of both hot and cold gas phases. Understanding the CGM is essential for piecing together the Milky Way's interactions with its cosmic surroundings. Satellite galaxies, companions on the outskirts. The outskirts of the Milky Way are home to dozens of satellite galaxies, ranging from the prominent Magellanic Clouds to faint ultra-faint dwarf galaxies. These companions orbit the Milky Way within its dark matter halo, contributing to its mass and interacting gravitationally with the larger galaxy. The Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, are the most massive and well-known satellites, connected to the Milky Way by a bridge of gas and stars known as the Magellanic Stream. These galaxies are currently undergoing tidal interactions with the Milky Way, which are stripping material from them and influencing their orbits. Ultra-faint dwarf galaxies, discovered in recent years, provide a unique window into the nature of dark matter and the early universe. These galaxies are thought to be dominated by dark matter, with only a few hundred to a few thousand stars. Their survival in the harsh environment of the Milky Way's outskirts is a testament to the stabilizing influence of dark matter. The edge of the Milky Way. One of the most intriguing questions about the galactic outskirts is where the Milky Way ends. The transition from the galaxy to intergalactic space is gradual, marked by a decrease in the density of stars, gas, and dark matter. This boundary, often called the virial radius, is where the gravitational influence of the Milky Way begins to wane. The virial radius of the Milky Way is estimated to be around 1 million to 2 million light-years, encompassing not only the visible galaxy, but also its extended dark matter halo and circumgalactic medium. Beyond this lies the local group, a gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and numerous smaller systems. The role of the outskirts in galactic evolution. The outskirts of the Milky Way are more than a passive boundary. They are an active participant in the galaxy's evolution. Mergers with satellite galaxies, the accretion of gas, and the influence of dark matter all shape the structure and dynamics of the galaxy. These processes drive the growth of the Milky Way, providing the raw materials for star formation and enriching the interstellar medium with heavy elements. The outskirts also serve as a bridge between the Milky Way and the larger universe. Through interactions with neighboring galaxies, the Milky Way exchanges material and energy, contributing to the cosmic web that connects galaxies across the cosmos. Unanswered questions and future exploration. Despite significant advances, the outskirts of the Milky Way remain one of its least understood regions. How did the stellar halo form? And what does it reveal about the galaxy's early history? What is the true shape and extent of the dark matter halo? And how does the Milky Way interact with its circumgalactic medium and satellite galaxies? Future missions, such as the Vera C. Rubin Observatory and the European Space Agency's Athena X-ray telescope, promise to shed light on these mysteries. By mapping the outskirts in unprecedented detail, these instruments will help astronomers unlock the secrets of the galaxy's farthest reaches. The Milky Way's frontier. The outskirts of the Milky Way are a cosmic frontier, a region where the galaxy's past, present, and future intersect. They are a place of discovery, revealing the remnants of ancient mergers, the influence of dark matter, and the interactions that shape the galaxy's evolution. As we explore these distant regions, we deepen our understanding of the Milky Way and its place in the universe, uncovering the threads that connect it to the vast cosmic web. The evolution of galactic arms. The spiral arms of the Milky Way, like celestial highways of stars, gas, and dust, are among the galaxy's most iconic features. These sweeping structures define the Milky Way's shape, hosting regions of intense star formation and some of the most luminous objects in the galaxy. Yet, despite their prominence, the origins, dynamics, and longevity of spiral arms remain topics of intrigue and ongoing research. Understanding the evolution of these arms offers insights into the forces that shape galaxies and the processes that sustain their beauty over billions of years. The nature of spiral arms. Spiral arms are not rigid structures like spokes on a wheel. They're dynamic, wave-like patterns that move through the galactic disk. Stars and gas enter and leave these arms as they orbit the galactic center. This distinction is crucial. Spiral arms are not collections of fixed material, but are instead regions of higher density, created and maintained by gravitational and hydrodynamic forces. The arms are sites of intense star formation, illuminated by young, massive stars that emit copious amounts of light before burning out in spectacular supernovae. The clustering of bright stars, combined with the glow of ionized gas, makes the arms stand out against the background of the galaxy's disk. Dust lanes, composed of cooler, denser material, often trace the leading edges of the arms, adding to their visual prominence. How do spiral arms form? The formation of spiral arms is a subject of considerable study, with several theories proposed to explain their origins. 1. Density wave theory. This widely accepted model suggests that spiral arms are patterns of higher density, similar to traffic jams on a highway. As stars and gas orbit the galactic center, they encounter these density waves, slowing down and temporarily concentrating in these regions. The arms appear brighter because the increased density triggers star formation, creating clusters of luminous young stars. 2. Self-propagating star formation. In this model, spiral arms are maintained by a feedback loop between star formation and supernovae. New stars form in gas clouds, and their intense radiation and stellar winds compress nearby gas, triggering the formation of additional stars. When massive stars explode as supernovae, they send shock waves through the surrounding medium, sustaining the cycle. 3. Tidal interactions. Some spiral galaxies exhibit arms that are induced by gravitational interactions with nearby galaxies. These tidal forces can create temporary or permanent spiral patterns, depending on the strength and duration of the interaction. In the Milky Way, the Magellanic Clouds and other satellites may contribute to the maintenance of its spiral structure. 4. Bar dynamics. The Milky Way's central bar, an elongated structure of stars and gas, plays a role in shaping its spiral arms. The bar channels material outward, creating resonances that amplify density waves in the disk. This mechanism helps sustain the arms over long time scales. The structure of the Milky Way's arms. The Milky Way is classified as a barred spiral galaxy, with a central bar and 4 primary spiral arms: the Perseus arm, the Sagittarius arm, the Scutum-Centaurus arm, and the outer arm. There are also smaller, secondary arms and spurs, including the Orion arm, which hosts the Sun and the Solar System. The arms are not evenly distributed. They vary in length, brightness, and star formation activity. The Perseus and Scutum-Centaurus arms are the most prominent, stretching across vast distances and hosting large concentrations of molecular clouds and star-forming regions. The Sagittarius and outer arms are more diffuse, but still contribute to the overall spiral structure. The location of the Sun in the Orion arm, a minor spur, provides a unique vantage point for studying the galaxy's arms. From Earth, the arms appear as faint, overlapping bands in the night sky, their full structure only becoming apparent through detailed surveys and modeling. The dynamics of spiral arms. Spiral arms are not static features, but evolve over time. The density wave theory predicts that arms are long-lived patterns, maintained by the rotation of the galaxy and the gravitational interactions between stars and gas. However, observations suggest that spiral arms can also form and dissipate on shorter timescales, influenced by internal and external factors. The motion of stars within the arms is governed by the galaxy's rotation curve, which describes how orbital velocity changes with distance from the center. The rotation curve of the Milky Way is relatively flat, meaning that stars in the outer disk orbit at nearly the same speed as those closer to the center. This rotation pattern contributes to the maintenance of the spiral structure, as stars repeatedly pass through the arms during their orbits. Gas dynamics also play a crucial role in the evolution of spiral arms. As gas flows into the arms, it becomes compressed, triggering the formation of molecular clouds and stars. This process, combined with the feedback from young stars, creates a self-sustaining cycle that keeps the arms active and luminous. The role of spiral arms in galactic evolution. Spiral arms are more than just decorative features. They are engines of galactic evolution. By concentrating gas and triggering star formation, the arms regulate the distribution of stars, elements, and energy within the galaxy. They are also sites of chemical enrichment, where the deaths of massive stars and supernovae distribute heavy elements into the interstellar medium. The arms influence the motion of stars and gas, creating patterns that extend far into the galactic halo. Stellar streams, remnants of disrupted star clusters and dwarf galaxies, are often shaped by the gravitational effects of the spiral arms. These interactions provide valuable clues about the galaxy's mass distribution and the influence of dark matter. The lifespan of spiral arms. The longevity of spiral arms depends on the processes that sustain them. Density waves, driven by the gravitational interactions within the galaxy, can persist for billions of years. However, individual features within the arms, such as star-forming regions and molecular clouds, have much shorter lifespans, evolving on timescales of millions of years. As the Milky Way ages, its spiral structure may change. The ongoing collision with the Andromeda Galaxy, expected in about 4.5 billion years, will likely disrupt the arms, transforming the Milky Way into a more elliptical or lenticular galaxy. Until then, the arms will continue to play a central role in the galaxy's evolution. Observing spiral arms. Advances in observational technology have provided detailed maps of the Milky Way's spiral structure. Radio telescopes, such as those used in the Hi-4Pi survey, map neutral hydrogen gas, revealing the large-scale distribution of the arms. Infrared telescopes, including the Spitzer Space Telescope, penetrate the dust that obscures visible light, providing a clearer view of the star-forming regions within the arms. The Gaia mission has revolutionized the study of the Milky Way structure by measuring the positions and motions of billions of stars with unprecedented precision. These data allow astronomers to trace the motions of stars within the arms, revealing their dynamics and evolution. Unanswered questions and future exploration. Despite significant progress, many questions about the evolution of spiral arms remain. How do density waves interact with other galactic components, such as the central bar and the dark matter halo? What triggers the formation of new arms? And how do external interactions shape their structure? Future missions, such as the Vera C. Rubin Observatory and the Square Kilometer Array, promise to address these mysteries. The beauty and purpose of spiral arms. The spiral arms of the Milky Way are more than just a striking feature. They are a testament to the galaxy's dynamic nature and its ability to sustain life and growth. By studying their evolution, we gain insights into the forces that shape galaxies across the universe, deepening our understanding of the cosmos and our place within it. The galactic year. The concept of a year is deeply ingrained in our understanding of time. On Earth, it represents the period it takes for our planet to complete one orbit around the Sun, a journey of approximately 365 days. But on a galactic scale, a year takes on an entirely different meaning. Known as a galactic year or cosmic year, it refers to the time it takes for the solar system to complete one full orbit around the center of the Milky Way. This staggering journey spans hundreds of millions of years, offering a unique perspective on the passage of time and the dynamics of our galaxy. What is a galactic year? The solar system is not stationary within the Milky Way. It orbits the galactic center at an average speed of about 828,000 kilometers per hour, 514,000 miles per hour. At this velocity, it takes approximately 225 to 250 million years to complete a single orbit. This duration is what we call a galactic year. While Earth's year is governed by the gravitational interaction between the planet and the Sun, the galactic year is influenced by the gravitational forces exerted by the Milky Way's central black hole, Sagittarius A*, and the combined mass of billions of stars, gas clouds, and dark matter that make up the galaxy. The solar system's path through the Milky Way. The solar system resides in the Orion Arm, a minor spur of the Milky Way's spiral structure, located about 27,000 light-years from the galactic center. As it orbits the center, the solar system's path is not a perfect circle, but an elliptical trajectory that also undulates slightly above and below the galactic plane in a wave-like motion. This vertical oscillation, known as the galactic wobble, occurs approximately every 30 million years and may have significant implications for Earth's history. The Milky Way itself is not static. Its spiral arms rotate at different speeds depending on their distance from the center, a phenomenon known as differential rotation. The solar system's motion is independent of the arms, meaning it periodically passes through them, encountering regions of higher density and increased star formation. The galactic year and Earth's history. To appreciate the scale of a galactic year, consider this. The Earth is about 4.54 billion years old, meaning our planet has completed roughly 20 galactic years since its formation. Each galactic year has witnessed significant events in Earth's history, linking the rhythms of the cosmos to the story of life on our planet. One galactic year ago, 225 to 250 million years, during the last completed galactic year, Earth was in the Triassic period, a time when dinosaurs were beginning to rise to prominence. The continents were joined in a supercontinent called Pangaea. 2 galactic years ago, 450 to 500 million years, the solar system was orbiting the Milky Way during the Ordovician period, when life thrived in Earth's oceans and the first primitive plants began to colonize land. 10 galactic years ago, 2.2 to 2.5 billion years, Earth's atmosphere experienced the Great Oxidation Event, a critical turning point driven by photosynthetic microorganisms that introduced oxygen into the atmosphere, paving the way for complex life. The alignment of these milestones with the solar system's galactic journey raises questions about whether cosmic factors, such as the solar system's position in the galaxy, have influenced Earth's climate, geology, and biological evolution. Cosmic hazards along the journey. The solar system's passage through the Milky Way is not without risks. As it moves through the galaxy, it encounters varying environments, including regions of higher star density, molecular clouds, and the spiral arms. These encounters can expose Earth to cosmic phenomena that may have profound consequences. Supernovae. Passing through regions of active star formation increases the likelihood of encountering supernovae, the explosive deaths of massive stars. The radiation and cosmic rays from nearby supernovae could impact Earth's atmosphere, depleting the ozone layer and influencing climate and biological evolution. Giant molecular clouds. Dense regions of gas and dust, such as giant molecular clouds, could disrupt the solar system's trajectory or affect the outer reaches of the solar system, potentially dislodging comets from the Oort cloud and sending them toward the inner solar system. Gamma-ray bursts. While rare, gamma-ray bursts, intense flashes of high-energy radiation, could pose a threat to life on Earth if they occur nearby. The likelihood of encountering such events may depend on the solar system's location within the galaxy. The galactic year and future prospects. As the solar system continues its orbit around the Milky Way, it is moving toward its next galactic year, set to complete around 225 to 250 million years from now. By that time, Earth will have undergone profound changes. The Sun, currently about halfway through its life cycle, will be older and more luminous, potentially causing the gradual warming and desiccation of Earth's surface. The solar system's long-term future is also influenced by the Milky Way's interaction with neighboring galaxies. In approximately 4.5 billion years, about 18 to 20 galactic years from now, the Milky Way will collide with the Andromeda Galaxy, initiating a transformative process that will reshape both galaxies. The solar system may find itself in a new galactic environment, orbiting within the merged structure often referred to as Milkomeda. Studying the galactic year. Understanding the galactic year is essential for exploring the interplay between cosmic and terrestrial phenomena. Advances in observational technology, such as the Gaia mission, have provided detailed maps of the Milky Way's structure and the solar system's motion, allowing astronomers to model its orbit with unprecedented accuracy. Simulations of the Milky Way's evolution offer insights into the forces that govern the galactic year, including the distribution of dark matter and the dynamics of spiral arms. These models also help identify regions of the galaxy that the solar system will encounter in the future, revealing potential risks and opportunities for studying cosmic phenomena. A cosmic perspective on time. The galactic year provides a humbling perspective on time and our place in the universe. While a human lifetime spans a mere fraction of an Earth year, let alone a galactic year, our understanding of these vast cycles connects us to the broader rhythms of the cosmos. The solar system's journey through the Milky Way is a reminder that Earth's history and future are inextricably linked to the galaxy's dynamics. The endless journey. As the solar system continues its orbit around the galactic center, it carries with it the legacy of billions of years of cosmic evolution. Each galactic year is a chapter in the story of the Milky Way, marked by the rise and fall of stars, the formation of planets, and the unfolding of life. The galactic year is not just a measure of time. It is a testament to the enduring motion of the cosmos, a journey that will continue long after humanity's time on Earth has passed. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.